Tonight, your eyes are open to the universe. The human eye receives light across a range so narrow that if the full electromagnetic spectrum were stretched across an entire football field from end zone to end zone, the slice your eyes can actually detect would be roughly the width of a single strand of thread. Everything else passes through you right now without your permission and without leaving anything your biology can register. Radio waves, X-rays, the infrared warmth radiating from other bodies in the dark, the gamma radiation still traveling from stars that died before this planet existed. You are not a window to the universe. You are a very specific filter. And yet tonight, in this quiet, we are going to try to move past the filter. Not by abandoning what we are, by following the evidence where our eyes cannot go until we arrive somewhere true. Your brain is not recording reality. It is producing it. This is not a philosophical position. It is a description of what is physically happening inside your skull right now while you lie still in the dark. Several times each second, your eyes make rapid, involuntary jumps called saccades. Each jump takes somewhere between 20 and 200 milliseconds. During that movement, the image falling on your retina is a blurred streak of motion. If your brain passed that blur forward into conscious experience, the world would look like a poorly handled camera. So your brain does something remarkable. It suppresses the visual signal entirely during the movement, then stitches the before and after together into a single seamless frame, with no gap visible, no blur registered, no evidence of the edit. You do not experience the jump. You experience the landing. And you do this several times, every second, every waking hour of your life, without ever noticing the cuts. What you call seeing is closer to a film editor's final cut than to raw footage. The raw footage exists. Your brain simply decides you do not need it. A reasonable response to this is, fine. So perception is imperfect. We already knew that. Glasses exist. Optical illusions exist. This is not new. But that response misses what is actually being described here. The problem is not that perception is imperfect. The problem is that the editing happens before you have any access to the unedited version. There is no moment where you can choose to see the blur. The suppression is not a bug you can work around. It is the process itself. What you receive as experience has already been shaped, trimmed, and assembled by systems you have no conscious access to, according to priorities you did not choose. The biologist Jakob von Uexküll gave this a name in the early 1900s. He called it the Umwelt. Every animal, he argued, does not live in the world. It lives in its own perceptual bubble, a selective slice of reality tuned by evolution to whatever that organism needs in order to survive and reproduce. A tick detects warmth and the chemical signature of butyric acid. A bat maps space through sound. A mantis shrimp reads 16 channels of color, where you read 3. None of them is wrong. Each is complete within its own bubble, and each is blind to everything outside it. The human umwelt is unusually wide. We process more sensory channels than most animals, and we have built instruments that extend our reach far beyond biology. But the instruments do not solve the underlying condition. They translate signals from outside the bubble into formats the bubble can process. The radio telescope converts radio waves into images a human eye can read. The spectrometer converts chemical signatures into graphs a human brain can parse. We are still inside the bubble. We have just learned to knock on the walls and listen to what knocks back. The visible light spectrum, the range your eyes can actually detect, occupies roughly 1 part in 10 million of the full electromagnetic spectrum. If you wanted to walk that ratio, Imagine a road stretching from New York City to Los Angeles and back again, roughly 9,000 kilometers total. The section you can see would be less than a meter long. Everything else on that road, every other form of electromagnetic radiation passing through your body right now, is happening in territory your biology was never built to enter. That narrow slice was not selected because it reveals the most about the universe. It was selected because it happens to be the range most useful for a medium-sized primate living on the surface of a planet with a star like ours, needing to find food, avoid predators, and read the faces of other members of its social group. The visible spectrum is not a window onto reality. It is a tool that helped a particular kind of body stay alive long enough to reproduce. What we call the universe, then, is a universe that has already been filtered through that tool. Every star catalog, every nebula photograph, every description of what space looks like is a description of what space looks like to an organism with this specific sensory range, this specific neural architecture, these specific editing systems running several times per second without pause. If the editing is invisible from the inside, how would we know what we are missing? The answer science has slowly worked toward is not reassuring in a simple way, but it is honest. You cannot step outside your umwelt directly. No organism can. But you can build instruments that detect signals your biology ignores. You can run experiments that reveal the editing process itself, and you can follow the math into territory where intuition breaks down entirely, and the only guide left is internal consistency. That is what physics has been doing for the last 4 centuries. Not escaping the bubble, learning the shape of it from the inside. Tonight, in this room, with your eyes closed, something useful is happening. The primary visual system is quiet. The saccadic editing has stopped. The retinal lag is no longer manufacturing a seamless present. What remains is a mind that is still capable of following an argument, still capable of holding a question open, still capable of reaching past the tools it was given. That is what we are doing here. Not seeing, reaching. If the editing is this thorough in the one sense we trust most, what does that imply about everything else we think we know by direct experience? Start with a number that almost no one talks about. Of the roughly 3 billion base pairs in the human genome, only about 1.5% actively codes for proteins. 1.5%. If you printed the entire human genome as a book, and that book ran to about 5,000 pages, the parts that directly instruct the body to build anything would fill roughly 75 pages. The rest would look, to a casual reader, like noise. For a long time, researchers called it junk DNA. That name turned out to be wrong, or at least premature. Some of the non-coding regions regulate when genes switch on and off. Some are remnants of ancient viral infections stitched into the genome over millions of years. Some have functions we are still working out. But the label is instructive regardless of its accuracy, because it reveals something about how human minds respond to information they cannot immediately parse. When we encounter signal we cannot read, our first instinct is to call it garbage. The writer Jorge Luis Borges imagined a library that contains every possible book. Not every book that has been written. Every book that could be written, given a fixed alphabet and a fixed page length. Every combination of letters, every arrangement of words, every possible sequence of sentences. The library is finite in the sense that it has a calculable number of volumes, but that number is so large it is effectively boundless. Somewhere in it is a perfect account of everything that has ever happened. Somewhere in it is a flawless proof of every mathematical theorem. Somewhere in it is a description of your life, accurate to the last detail, written in a language you can read. And surrounding all of those, in every direction, are books that are pure gibberish. Pages and pages of random letters that contain no meaning, no structure, no coherent sentence anywhere in their length. The ratio of meaningful books to meaningless books in Borges' library is not close. It is not 10 to 1 or 1 to 1,000. The meaningful books are so vanishingly rare within the total that if you chose a volume at random, the probability of it containing a single grammatical sentence in any human language would be, for all practical purposes, 0. The library is almost entirely noise. The signal is almost impossible to find. This is not just a thought experiment about books. It is a description of the problem that every information processing system in the universe faces. When the first self-replicating molecules appeared on early Earth, somewhere around 4 billion years ago, they existed in a chemical environment that was generating an enormous variety of random sequences. RNA molecules folding into different shapes, reacting with different substrates, copying themselves with different error rates. Most of those sequences did nothing useful. Most folded into shapes that could not catalyze anything, could not copy themselves reliably, could not maintain any structure against the entropy pulling them apart. They were noise in the library. The ones that happened to do something, that happened to catalyze a useful reaction or copy themselves slightly more faithfully, those persisted long enough to generate more copies. Evolution is not a process that finds the right answer. It is a process that applies selection pressure to an enormous number of random variations and retains the ones that function. It is, in a precise sense, a librarian, not one that reads every book and judges its quality, but one that watches which books get picked up and read, which ones sit on the shelf untouched, and gradually removes the ones that no one ever opens. Over billions of years, that filtering process produced the 1.5%, the 75 pages of instructions that build a human body. If meaning is this rare in the space of possible sequences, what does it say about how hard it is to find and how easy it is to lose? Language is the same problem at a different scale. Every sentence you have ever spoken or heard is a tiny island of structure in a vast sea of possible sound sequences. The difference between a sentence that conveys an idea and a sequence of sounds that conveys nothing is not always large. A few phonemes shifted, a few words rearranged, and the signal degrades into noise. And yet language has persisted and diversified because the sequences that work, the ones that reliably transfer meaning from one mind to another, get used again. The ones that fail to transfer meaning get abandoned. The library of human language is enormous, but it is a tiny fraction of the space of possible utterances. I keep returning to what this implies about the act of listening. Right now, you are doing something that required billions of years of filtering to make possible. Your auditory system is taking a continuous stream of vibrations in the air and extracting structured information from it. The vibrations that carry no information are discarded automatically. The ones that pattern match to language are routed to the language processing centers. The ones that match emotional tone are routed elsewhere. This sorting is happening below the threshold of awareness, faster than thought, drawing on a system refined by every generation of your ancestors who successfully communicated with another member of their group. You are not passively receiving signal. You are actively filtering noise. The same way evolution filtered RNA sequences. The same way a librarian filters a shelf. The uncomfortable implication of all this is that meaning is not a property of the universe. It is a property of systems that are capable of distinguishing signal from noise, and those systems are rare, fragile, and expensive to maintain. The universe generates noise effortlessly, in every direction, at every scale. Generating meaning requires something to do the work of filtering, and that something has to persist long enough to do it. Which is why the existence of a mind capable of asking whether any of this matters is, in the most literal sense, improbable. Not metaphorically improbable, statistically improbable, given the ratio of functional sequences to non-functional ones in any space of possibilities large enough to contain the alternatives. You are the signal that survived the library. It is a description of a physical process that took approximately 4 billion years and an uncountable number of failed variations to produce. If meaning is this hard to generate and this easy to lose, what is the oldest surviving signal we know of in the universe, and what can it tell us about what persists? Something left this planet in the late summer of 1977 and has not stopped moving since. It is roughly the size and weight of a compact car. It carries a 12-watt transmitter, about as powerful as a refrigerator light bulb. And right now, traveling at about 17 kilometers per second, it is farther from Earth than any human-made object has ever been. The signal it sends back takes more than 22 hours to reach us, traveling at the speed of light. Voyager 1 is not the most sophisticated machine we have ever built. It is not the fastest, not the most powerful, not the most capable. What it is the most distant. And that distance, accumulated over nearly 5 decades of uninterrupted travel, has made it something that was not in the mission plan. It has become a philosophical object. Consider what it is carrying. Bolted to its frame is a gold-plated copper disc, 12 inches across, containing sounds and images selected to represent life and culture on Earth. Greetings in 55 languages. Music ranging from a Azerbaijani folk song to a Chuck Berry recording. The sound of wind, rain, surf, a mother's first words to a newborn child. Brainwaves recorded from a young woman thinking about her memories, her hopes, the people she loved. Mathematical diagrams intended to help a hypothetical reader locate where the disc came from. A map home, sent with a message that assumed someone would be there to receive it. The people who made those choices had no way of knowing whether any of it would ever be found. The probability that Voyager 1 will come within even 2 light-years of another star system in the next 40,000 years is extremely small. The probability that any civilization capable of retrieving and decoding a gold disk exists within range is unknown in a way that cannot be resolved with current data. The people who chose those sounds and images knew all of this. They sent it anyway. I find that decision harder to dismiss than it might first appear. It is easy to frame it as optimism, or as public relations for a space program that needed popular support. Both of those things may be true, but there is something else in it that resists that framing. The act of selecting what to include, of deciding that a mother's first words to her child belongs on a message to the universe, requires a judgment about what matters. Not what matters for survival, not what matters for scientific advancement. What matters in a way that might still matter to something entirely unlike us, across a distance we cannot meaningfully imagine. That is an ethical act. Possibly the most compressed ethical act in human history. Now set that against what Voyager 1 will actually encounter. In about 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445, a red dwarf in the constellation Camelopardalis. 1.6 light-years is still an enormous distance, roughly 10 trillion kilometers, close in galactic terms but not close enough for any realistic interaction. After that, Voyager will continue into the void between stars, where it will travel for millions of years without passing near anything. The gold disk, sealed against the vacuum, will remain intact for an estimated billion years, longer than the entire history of complex life on Earth. In 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, likely engulfing Mercury, Venus, and possibly Earth. Everything that remains of human civilization at that point, every archive, every structure, every trace of biology, will be absorbed into the expanding envelope of a dying star. Voyager will not be. It will still be moving. carrying a recording of a young woman's brainwaves and the sound of rain on a surface that no longer exists. What Voyager 1 represents, in purely physical terms, is the persistence of a pattern beyond the system that generated it. The civilization that built it will not survive the sun. The probe almost certainly will. The information it carries, the greetings, the music, the brainwaves, those patterns will outlast their origin by an interval so large that the word outlast stops conveying anything useful. There is a question inside that physical fact that I am not sure how to resolve. If a pattern persists but there is no longer anyone for whom it carries meaning, does the meaning persist with it? A recording of a mother's first words to her child, traveling through interstellar space 1 billion years from now, with no human ear remaining to hear it, and no human mind to understand what a mother is. Is it still a message? Physics says the pattern is intact. The grooves in the gold disk will still encode the same vibrations. The information content, in the technical sense, is preserved. But information in the technical sense and meaning in the human sense are not the same thing. Meaning requires a receiver. It requires a mind that can map the pattern onto something it already understands. Without that, you have structure, but not significance. The people who built the golden record knew this. They were not confused about what they were doing. They were making a choice that acknowledged the difference between the two and proceeded anyway, because the act of sending mattered independent of whether it was ever received. The message was also, and perhaps primarily, for us, a record of what we thought was worth keeping, a judgment encoded in gold and launched into the dark, about what human experience contains that might be worth preserving even after humans are gone. That judgment is still out there, moving at 17 kilometers per second, getting farther every second you lie still in this room. If the only surviving record of what we were is a pattern traveling through empty space with no one left to read it, what does that say about what we owe each other while we are still here to receive it? For most of recorded history, there was a star in the northern sky that people did not trust. It sits in the constellation Perseus, about 93 light-years from Earth. That distance means the light reaching your eye tonight left that star sometime around 1932, before the Second World War, before penicillin was widely available, before the first programmable computer existed. You are looking at old light. But the discomfort people felt about this star was not about its distance, it was about its behavior. Every 2 days and 21 hours, Algol dims. Not dramatically, not catastrophically, but measurably, reliably, and in an era before electric light, visibly to anyone who watched the sky with enough patience, it would fade to about 1/3 of its normal brightness over the course of about 5 hours. Hold there briefly, then recover. Then, roughly 2 days and 21 hours later, it would do it again. Same duration, same depth, same recovery. A rhythm that did not match anything else in the sky. The ancient Egyptians appear to have noticed. A calendar fragment known as the Cairo calendar, dating to around 3,200 years ago, contains annotations that some researchers believe track Algol's cycle alongside lunar and solar periods. If that interpretation is correct, it would make Algol the oldest variable star in the observational record, documented more than a millennium before the telescope existed. The Arabic astronomers who named it called it Ras al-Ghul, the head of the demon. Medieval European astronomers inherited that name and the unease that came with it. The Chinese records from roughly the same era refer to the star using a term that translates roughly as accumulated corpses. Every culture that watched carefully enough to notice the dimming reached, independently, for language that implied something was wrong, something dying, something predatory, something that violated the expected order of lights that were supposed to stay fixed and reliable in the dark. The actual explanation, worked out in 1889 by the German astronomer Hermann Karl Vogel using spectroscopic measurements, is in some ways stranger than the mythology. Algol is not one star. It is two, orbiting each other so closely that from Earth they appear as a single point of light. Every time the dimmer of the two passes in front of the brighter one from our line of sight, we see a partial eclipse. The rhythm ancient observers tracked across centuries is not a sign, not a curse, not a cosmic irregularity. It is geometry. Two bodies, locked in mutual orbit, periodically blocking each other's light as seen from a specific vantage point, 93 light-years away. But the geometry is only the beginning of what is happening in that system. The larger star in the Algol system is in the process of losing mass to its companion. Not through any catastrophic event, not through collision or explosion, but through a slow, continuous process driven by nothing more dramatic than the difference in gravitational pull across the diameter of the larger star. The side of the star facing its companion is pulled more strongly than the side facing away. Over time, that differential stretches the star slightly out of round, and material from its outer layers flows across a boundary called the Roche lobe and accretes onto the companion. The smaller, denser star is eating the larger one. Slowly, continuously, one layer at a time. This process has been going on long enough that it has produced a result that initially seems paradoxical. In most binary systems, the more massive star evolves faster, ages faster, and reaches a later evolutionary stage first. But in Algol, the less massive star is actually the more evolved one. It has already passed through its giant phase and contracted back down. The reason is that when it was the more massive star, it transferred so much of its own mass to its companion that it effectively reversed the mass ratio of the system. The star that is currently eating was once the one being eaten. The predator and the prey traded places over millions of years, and what we see now is the current snapshot of a process that has been running longer than our species has existed. What stays with me about this is not the mechanism itself, accurate and elegant as it is. It is the gap between what the mechanism actually is and what every human culture that observed it reached for to describe it. Accumulated corpses, the demon's eye, a star that could not be trusted. The discomfort was real. The watching was real. The records, in some cases maintained across centuries of careful observation, were real. All of that genuine attention was pointed at a physical process that had nothing in it of malice, nothing of intention, nothing of warning. Two stars in mutual orbit, one slowly drawing material from the other along a path dictated entirely by the mathematics of gravity and fluid dynamics, periodically eclipsing each other as seen from a small planet that happened to be positioned at the right angle to notice the dimming. The demon was a geometry problem. The accumulated corpses were an accretion disk. And yet I do not think the people who watched Algol for centuries and felt that something was wrong were simply mistaken in an interesting way. They were doing something that turns out to be deeply human and not entirely irrational. When you observe a pattern that deviates from background regularity, especially a repeating pattern with a consistent period, the most efficient response is to treat it as potentially significant until proven otherwise. The cost of ignoring a real signal is higher than the cost of over-interpreting a meaningless one. Evolution shaped nervous systems that would rather see a pattern that is not there than miss one that is. The ancient astronomers who tracked Algol were running exactly that algorithm, applied to the sky. What changed was not the observation. What changed was the framework available for interpreting it. Once spectroscopy made it possible to detect that Algol was actually two light sources moving relative to each other, the eclipse interpretation became available. Once orbital mechanics and stellar physics developed far enough to model mass transfer between close binary companions, the fuller picture came into focus. The observation stayed the same across 3,000 years. The explanation changed. because the tools for building explanations changed. That is worth pausing on, because it describes something about the nature of the whole project we are engaged in tonight. We are not looking at the universe with better eyes than the people who named Algol the demon star. We are looking at it with better frameworks, the raw data. Photons arriving at a retina or a detector is not categorically different from what they had. What is different is the set of structures we can use to make sense of what those photons are telling us. And those structures are still being built. There are signals in the sky right now that we are tracking carefully, marking as anomalous, reaching for language to describe that a future framework will resolve into something as geometrically clean as an eclipsing binary. We do not know which signals those are. We are in the position of the Cairo calendar scribe, noting the rhythm, not yet having the framework to explain it. If every culture that watched Algol reached for the language of death and predation before they had the tools to see what was actually happening, what does that tell us about the explanations we are currently most confident in? For most of human history, the stars had no distance. They were lights, fixed points on a surface that rotated overhead. The ancient Greeks debated whether they might be holes in a dark sphere or fires burning at some unspecified remove, but the debate was philosophical, not empirical, because no one had a method for actually measuring how far away a light source is when you cannot walk to it, cannot send a signal and wait for a reply, cannot do anything except observe it from a single point on the surface of one small planet. The problem is genuinely difficult in a way that is easy to underestimate. Distance, for most of human experience, is something you measure by moving. You pace it out. You time how long it takes to cross. You use the parallax your two eyes provide to judge depth up to a few tens of meters. Beyond that range, direct perception fails and you need instruments. But what instrument do you use for a light that is years away, when you cannot move the instrument anywhere near the scale of the distance you are trying to measure? The answer Friedrich Bessel arrived at in 1830 was one of those rare ideas that transformed a seemingly impossible problem into something that could actually be measured. Bessel was a German astronomer and mathematician who had left school at 14 to become a merchant's apprentice, taught himself astronomy and higher mathematics in his spare time, and by his mid-20s had recalculated the orbit of Halley's Comet with enough accuracy that the astronomer Heinrich Olbers arranged for him to receive a formal position. By the time he turned to the problem of stellar distances, he had spent decades making precise measurements of star positions, developing the mathematical tools to correct for instrumental errors, atmospheric distortion, and the tiny wobbles introduced by the Earth's own motion. His method used the Earth itself as a measuring instrument. The Earth orbits the Sun at a distance of about 150 million kilometers. That means, in January, when the Earth is on one side of its orbit, and again in July, when it is on the opposite side, the planet has moved approximately 300 million kilometers relative to where it was 6 months earlier. That is a very long baseline, and if you photograph a nearby star against the background of much more distant stars in January, then photograph it again in July, a nearby star will appear to have shifted slightly against that background, the same way a finger held up in front of your face appears to shift against the wall behind it when you alternate closing each eye. The amount of shift tells you the distance. The shift is extraordinarily small. Even for the nearest stars, it amounts to less than 1 arcsecond, which is 1/3600th of a degree, which is roughly the angle subtended by a dime viewed from about 3.5 kilometers away. Measuring it in Bessel's era required years of meticulous observation. Instruments sensitive enough to detect motions far smaller than any previous astronomical measurement, and the mathematical framework to separate the genuine parallax shift from dozens of other sources of apparent stellar motion. Bessel chose a star called 61 Cygni, a faint star in the constellation Cygnus that he had noticed moving unusually quickly against the background of more distant stars, which suggested it was relatively nearby. After 18 months of careful measurement, he announced a parallax of about 3/10 of an arcsecond. That corresponds to a distance of about 10.5 light years. The modern measurement is 11.5 light years, which means Bessel's result, made with instruments that would look primitive by current standards, was off by less than 10%. 10.5 light years. Light travels at about 300,000 kilometers per second. In a year, it covers roughly 9.5 trillion kilometers. So 10.5 light years is approximately 100 trillion kilometers. If you wanted to drive there at highway speed, assuming a car that never needed fuel or maintenance and a road that extended through interstellar space, the journey would take roughly 115 billion years. The current age of the universe is about 13.8 billion years. You would need to drive for roughly 8 times the current age of the universe to cover that distance. And 61 Cygni is close. By the standards of our galaxy, it is practically next door. What Bessel's measurement did, beyond establishing a number, was force a confrontation with what that number meant. Before 1838, the distance to the stars was unknown, but not viscerally felt as unknown, because there was no measurement to give it scale. After 1838, there was a number, and a number, even an incomprehensibly large one, is different from a mystery. A number sits in the mind differently. It insists on being related to other numbers. 100 trillion kilometers insists on being compared to the distance across a city, or across a country, or across the planet. And every comparison fails in the same direction. The star is so much farther than any of those things that the comparisons stop helping almost immediately. This is the moment I keep returning to when I think about what Bessel actually accomplished. Not the measurement itself, which was a technical achievement of the first order, but the aftermath of the measurement, the fact that once you have a number, you are committed to it. You cannot unknow it. The universe that existed before 1838, the universe in which stellar distances were simply unknown, was in a strange way more comfortable than the universe that existed after, in which they were known, and the knowing was staggering. Bessel gave humanity its first accurate sense of how far away the nearest stars are, and what that gift contained, inseparably, was the first accurate sense of how alone we are. The light year was not invented as a unit of measurement before stellar distances were known. There was no need for it. The meter, the kilometer, the astronomical unit measuring the Earth-Sun distance, these were sufficient for everything within reach. The light year became necessary only when the numbers got too large for existing units to carry without becoming absurd. A new unit of measurement was required, not because the universe changed, but because human knowledge caught up to a scale that had always been there and now had to be spoken about in terms that did not collapse under their own weight. Units of measurement are not neutral. They carry the history of the understanding that required them. The light year is not just a convenient shorthand. It is a record of the moment when human beings first had to take seriously the possibility that the universe is incomparably larger than anything their previous frameworks had prepared them for. Every time someone uses the term casually, they are standing on top of 18 months of Bessel's careful measurements without knowing it. The star 61 Cygni is still there. It will be there, essentially unchanged, for billions of years after this conversation ends. The light leaving it tonight will reach Earth in 11.5 years. If someone is watching carefully from a planet orbiting 61 Cygni right now, the light they are receiving from Earth left here in approximately 2013. They are watching a version of this planet from over a decade ago. Distance at stellar scales is also time. And time at stellar scales means that every observation is a message from the past, sent before the observer existed to send it. If measuring the distance to a single nearby star required building an entirely new unit of measurement just to speak about it without absurdity. What happens to our frameworks when the distances involved are not 11 light years, but 11 billion? In 1957, 4 physicists published a paper that should have changed everything about how human beings think about each other. It did not, quite. But the paper was real, the physics was correct, and what it established is still true tonight, while you lie in the dark breathing air that your lungs are converting into carbon dioxide that will eventually be absorbed by plants that will eventually die and decompose and return their parent advivance, carbon, to a cycle that has been running since before this planet had oceans. The carbon in your body has a history, and that history does not begin on Earth. The paper, known by the initials of its 4 authors, established through spectroscopic observation and nuclear physics calculations that the elements heavier than hydrogen and helium, every element your body contains, were synthesized inside stars, not near stars, not around stars. Inside them, in the nuclear reactions occurring at stellar cores where temperatures reach tens of millions of degrees and pressures are high enough to force atomic nuclei into configurations they would never achieve anywhere else in the universe. The mechanism works like this. A star begins its life fusing hydrogen into helium in its core. That process releases energy, which creates outward pressure that balances the inward pull of gravity, and the star holds its shape. When the hydrogen in the core runs out, the core contracts under gravity, heats up further, and begins fusing helium into carbon and oxygen. Then, in more massive stars, the carbon fuses into neon and magnesium, the neon into oxygen and silicon, the silicon into iron. Each stage requires higher temperatures than the last. Each stage runs faster than the last. The iron stage, in a star massive enough to reach it, runs for roughly 1 day before the core collapses. What follows is a supernova, an explosion releasing more energy in seconds than the sun will emit across its entire 10 billion year lifetime. And in that explosion, the elements heavier than iron are forged and scattered into the surrounding space. The iron in your blood was made in the core of a star that ended in that kind of explosion. The oxygen in your lungs, the calcium in your bones, the phosphorus in the DNA carrying the instructions for every protein your body has ever made. All of it was assembled in stellar interiors over timescales ranging from millions to billions of years, scattered by stellar deaths, and eventually incorporated into the molecular cloud that collapsed to form this solar system roughly 4.5 billion years ago. One of the 4 authors of that paper was Margaret Burbidge. She was, by the mid-1950s, already recognized among the astronomers who had worked with her as an exceptional observer and a rigorous analyst. She had a particular skill with spectrographs, the instruments that split starlight into its component wavelengths and reveal the chemical composition of a star's atmosphere. The team she worked with, including her husband Geoffrey Burbidge, William Fowler, and Fred Hoyle, spent 2 years assembling the observational data and theoretical framework that the paper required. The work was hers as completely as it was any of the others. The paper transformed stellar astrophysics. The theory it established, nucleosynthesis in stars, became the foundation on which essentially everything we now understand about the chemical evolution of the universe is built. William Fowler received the Nobel Prize in Physics in 1983 for his contributions to this work. Margaret Burbidge did not. She had, by that point, also been denied the Annie Jump Cannon Award from the American Astronomical Society, an award specifically created to recognize women in astronomy, on the grounds that she was not sufficiently in need of the encouragement the award was intended to provide. She declined the award publicly and stated that it should not exist as a separate category for women at all. I want to stay with that for a moment, not because it is an unusual story in the history of science, but precisely because it is not. The same physics that established we are all made of the same stellar material, that the iron in one person's blood and the iron in another person's blood came from the same category of stellar explosions governed by the same nuclear physics, was developed in a professional environment that treated contributors differently based on characteristics that have nothing to do with the physics. The science said one thing about human equivalence. The institution practiced another. The physical fact established in that 1957 paper is that the atoms composing your body and the atoms composing the body of any other person on this planet share a common origin in stellar nucleosynthesis. The carbon in your left hand and the carbon in the left hand of someone on the opposite side of the planet were both assembled in stellar cores, both scattered by supernovae, both incorporated into the same molecular cloud, both processed through the same planetary chemistry over the same 4.5 billion years. The difference between any two human bodies at the level of elemental composition and atomic history is negligible. That is not a poetic observation. It is a description of what spectrographic measurements and nuclear physics calculations have established about the provenance of matter. What it does not automatically produce is the ethical conclusion that seems to follow from it. Knowing that we are made of the same star stuff does not, by itself, generate the behavior that recognition might seem to demand. Margaret Burbage's colleagues knew the same physics she did. The knowledge was shared. The behavior was not uniform. There is something worth sitting with in that gap, not as a reason for despair, but as a precise description of a problem. The universe, at the level of nuclear physics, does not distinguish between the atoms in one person and the atoms in another. The distinction exists only at the level of the systems those atoms compose. The biological systems, the social systems, the institutional systems that assign different value to different arrangements of matter that are, at the atomic level, interchangeable. The injustice is not written into the physics, which means it is not inevitable, which means it is a choice, even when it presents itself as something else. Every atom of iron in your blood was forged in a star that died before this planet formed. That iron has been part of rivers, part of ancient seafloor sediment, part of organisms that no longer exist before it arrived in you. It will leave you eventually and become part of something else. The boundary you experience as your skin is real and important at the scale of biology and experience, but at the scale of atomic history, it is temporary and permeable in ways that daily life does not make obvious. The physicist who established this is still alive. Margaret Burbage was born in 1919 and spent decades continuing to do productive work in observational astronomy after the paper that should have made her a household name. The stellar explosions that forged the iron in her blood and in yours are still happening in other galaxies right now, and the material they scatter will eventually become part of systems we cannot predict and organisms we cannot imagine. The process does not stop. It has never stopped. It ran for billions of years before anything on this planet was capable of noticing it, and it will run for billions of years after. If the atoms in every human body share the same stellar origin, and that fact was established by a team whose members were not treated as sharing the same professional worth, what does it mean to take the physics seriously while failing to take its implications seriously? There is a cloud of gas and dust in the constellation Orion that has been forming stars for millions of years without any awareness that anyone is watching. It will continue forming stars for millions of years after every human observer is gone. The process does not require an audience. Gravity pulls molecular hydrogen together. The cloud collapses under its own weight. Pressure and temperature at the center rise until nuclear fusion ignites and a new star begins burning. This has happened thousands of times in that region alone. It is happening right now, in several locations within that cloud simultaneously, in the dark, between the stars that are already visible. We named a piece of that cloud after a horse. The Horsehead Nebula is a dark column of dense gas and dust rising against a brighter region of ionized hydrogen behind it. The column is roughly 4 light-years tall, which means that if you replace the distance from Earth to the nearest star with the height of this single cloud formation, it would just about fit. The shape, when photographed from Earth, suggests the head and neck of a horse in profile, and so that is what we called it. The name was assigned by the Scottish astronomer Williamina Fleming in 1888, while she was working at the Harvard College Observatory examining photographic plates. Fleming had been hired initially as a housekeeper, was then brought into the observatory as a human computer, classifying stellar spectra for 25 cents an hour, and over the course of her career, catalogued more than 10,000 stars and identified numerous nebulae. The Horsehead was one entry in a long sequence of careful observations made by a woman who was paid less than a janitor for work that shaped our understanding of the sky. She named it after a horse because it looked like a horse. The name stuck. The interesting question is not why she chose that name. The interesting question is why the shape looked like a horse to her, and why it still looks like a horse to everyone who sees it now, and what that reflex reveals about the minds doing the looking. The human visual system contains a region called the fusiform face area, located in the temporal lobe, that responds preferentially to faces and face-like configurations. It activates not just for actual faces, but for arrangements of features that approximate the general geometry of a face, two roughly symmetric elements above a central element, with a border suggesting a containing shape. It activates for faces in clouds, faces in wood grain, faces in the shadows on a cratered moon. This is not a malfunction. It is the system working as designed. For most of human evolutionary history, the cost of missing a face, failing to recognize another person, failing to detect the presence of a predator that has a face, was potentially fatal. The cost of seeing a face that was not there was almost always negligible. A brain wired to err heavily toward face detection would, on average, survive better than a brain wired for precision, so that is the brain we have. One that finds faces in gas clouds 4 light-years tall, in the patterns of bark on a tree, in the arrangement of craters on a body 238,000 miles away. Pareidolia is the technical term for this, the perception of meaningful patterns, usually faces or figures, in random or ambiguous visual data. It is not a quirk or an error. It is the signature of a system optimized for a specific kind of detection in a specific kind of environment, running on data that system was not designed to process. The Horsehead Nebula is not ambiguous in the way a face in clouds is ambiguous. It is a dense column of molecular gas. The horsehead shape is a silhouette produced by the geometry of the column against the illuminated region behind it, the result of differential opacity, not of any organizing principle that intended the shape. The horse is entirely in the observer. And yet the name persists. Fleming chose it in 1888, and it is still the name used in every current catalog, every research paper, every public description of that object. We have known for well over a century what the Horsehead actually is, that it is a stellar nursery, a region where gravitational collapse is producing new stars, a pillar of cold, dense gas where the conditions for nuclear ignition are slowly being met. We know the horse is not there. We kept the name anyway. There is something honest in that choice, even if it was not made consciously. The name records the fact of the observation as much as the object observed. It says, a person looked at this and saw a horse, and that fact about the looking is worth preserving alongside the facts about the gas. The catalog entry is not just a description of a nebula, it is a description of a human mind encountering a nebula and doing what human minds do. The broader pattern is everywhere in astronomy. The Crab Nebula is not a crab. The Eagle Nebula contains a formation called the Pillars of Creation that are pillars only in the sense that they are tall and roughly vertical from our viewing angle. The Butterfly Nebula looks like a butterfly from Earth. From a different angle, the same structure would suggest nothing of the kind. Our entire named catalog of the sky is a record of what the sky looks like to organisms with this particular visual system, viewed from this particular position shaped by this particular evolutionary history. The catalog is also a self-portrait. This matters beyond the aesthetic observation that humans find human shapes in inhuman things. It matters because the same pattern recognition system that names gas clouds after horses is the one doing the science. The same fusiform face area that makes you see a horsehead in a stellar nursery is part of the neural architecture that reads graphs, interprets spectra, notices anomalies in data. The instruments extend the reach of perception far beyond what biology provides, but the interpretation of what the instruments report passes through a mind shaped by the same evolutionary pressures that make clouds look like animals. Good scientific practice is largely a set of techniques for catching the places where that mind leads you wrong. Blind analysis, where you do not look at the result until the procedure is locked. Peer review, where other minds shaped by similar pressures but oriented by different specific experiences check the interpretation. Statistical thresholds that require a signal to be strong enough that it would be extremely unlikely to arise from noise alone. These are not ways of eliminating the human pattern recognition system from science. They are ways of disciplining it, of building structures around it that catch its characteristic errors before they propagate into the record. The Horsehead Nebula is being observed right now by instruments that detect wavelengths far outside the visible range. Infrared observations reveal the warm dust being heated by nearby young stars. Radio observations map the molecular hydrogen in the dense core where new stars are forming. X-ray observations detect the radiation from the most recently ignited stellar objects embedded in the cloud. None of those observations look like a horse. They look like temperature gradients, spectral lines, emission peaks at specific frequencies. They are, arguably, more accurate representations of what is actually there. They are also much harder for the pattern recognition system to engage with, which is why the image in visible light, the one that looks like a horse, remains the one most people have seen. We navigate toward what we can recognize. Even when we know the recognition is partial, even when we have access to representations that are more complete but less familiar, the horse in the gas cloud keeps pulling attention because attention was built to follow that shape long before anyone knew that attention was built at all. In the dark right now, with eyes closed, the pattern recognition system is quieter than it is during the day. The fusiform face area is not being driven by incoming visual data. The shapes it finds are coming from memory and association, not from the world outside. This is one of the ways that the mind at rest is different from the mind at work. Not absent, not switched off, but running on internal signal rather than external, building patterns from what is already stored rather than from what is arriving. The horsehead will still be there when you open your eyes, still forming stars, still shaped from this angle like a horse, still carrying the name a woman assigned to it while being paid less than a janitor for work that mattered. The stars it is producing now will still be burning in 100 million years. No one alive today will see them fully formed. If the names we give to things in the sky are records of the minds that looked at them, what does it mean that the oldest surviving records we have are of a star whose light changes on a rhythm ancient observers found threatening, and of objects whose shapes reminded them of animals they knew? There is a star about 200 light-years from Earth that created a genuine crisis in astrophysics, not because it exploded, not because it behaved unexpectedly, but simply because of how old it appeared to be. The crisis was quiet, as scientific crises often are. No announcement, no emergency, just a number that would not fit, sitting in the data, refusing to be explained away. The star is catalogued as HD 14283. Astronomers who work with it regularly call it the Methuselah star, after the biblical figure said to have lived 969 years, the oldest human lifespan recorded in that tradition. The name was not chosen casually. Early estimates of the star's age came back at around 16 billion years. The universe, by the best measurements available, is approximately 13.8 billion years old. The star appeared to be older than everything that contained it. A reasonable response to that result is that something in the measurement must be wrong. That is also the correct scientific response. The question is which measurement and why, and what fixing it reveals about the limits of the tools being used. To understand what went wrong, you need to understand how astronomers determine the age of a star at all, because there is no direct method. You cannot take a core sample from a star the way you date a tree or a rock formation. What you can do is measure the star's current properties precisely: its luminosity, its temperature, its chemical composition, and then compare those measurements against theoretical models of how stars of that type evolve over time. The model tells you where in its life cycle a star with those properties should be. The age is inferred from that position, not measured directly. HD 14283 is what astronomers call a population 2 star, one of the oldest class of stars in the galaxy. Population 2 stars formed very early in the universe's history, before successive generations of stellar death had enriched the interstellar medium with heavy elements. They contain very little of anything heavier than helium, because when they formed, very little of anything heavier than helium existed. The chemical composition of HD 14283 reflects that ancient origin. Its iron content is roughly 1,000th that of the Sun. Its surface shows the fingerprints of a time when the galaxy was young enough that most of the heavy elements we take for granted had not yet been forged. The age estimate of 16 billion years came from applying stellar evolution models to those measured properties. The problem, as it turned out, was not with the star. It was with one of the inputs to the model. Determining the absolute age of a star from its properties requires knowing its exact distance, because luminosity, how bright a star actually is rather than how bright it appears from Earth, depends on distance in a way that cannot be separated from the other measurements without knowing where the star actually sits in space. The distance to HD 14283 had been measured, but when researchers reanalyzed the data with more precise techniques and corrected for a subtle systematic error in how the parallax measurements had been processed, the distance came out slightly different. Not dramatically different. Slightly. That slight difference, fed back through the stellar evolution models, shifted the age estimate down to approximately 14.5 billion years, with an uncertainty range of about 800 million years in either direction. The lower end of that uncertainty range overlaps with the age of the universe. The star is almost certainly not older than its container. It is simply old enough that the measurement uncertainties in both the stellar age and the cosmic age allow for a range that briefly overlapped in a way that looked like a paradox. The paradox dissolved not because anyone discovered new physics, but because someone looked more carefully at the existing data and found a small, correctable error in a measurement that had seemed reliable. In the early decades of the 20th century, the Harvard College Observatory employed a group of women paid 25 cents an hour to examine photographic plates of stellar spectra and classify stars according to their absorption line patterns. These women processed hundreds of thousands of stellar observations by hand, developing and applying the spectral classification system that is still used today. Annie Jump Cannon alone classified around 350,000 stars over her career. The spectral data she and her colleagues compiled became the foundation on which everything we now know about stellar populations, stellar evolution, and stellar ages is built. Without that foundation, the stellar evolution models that produce the Methuselah age estimate would not exist. Without those models, there would be no framework for recognizing that a 16 billion year age was anomalous. Without recognizing the anomaly, there would have been no investigation, no correction, no resolution. The entire chain of reasoning that led to understanding why HD 14283 is not actually older than the universe runs back through decades of careful, underpaid, largely uncelebrated classification work. What the Methuselah star actually represents, stripped of the apparent paradox, is one of the oldest surviving objects in the observable universe. It formed within a few 100 million years of the Big Bang, in the earliest period of star formation, Wishost, when the raw material available was almost entirely hydrogen and helium left over from the first few minutes of the universe's existence. It has been burning for so long that the galaxy it formed in looks almost nothing like the galaxy it inhabits now. The Milky Way of 14 billion years ago was a smaller, less structured collection of early stars and gas clouds. The spiral arms, the disk, the central bulge. These features developed over billions of years of mergers, accretion, and gravitational settling. HD 14283 was already old before any of that structure existed. 200 light-years is close enough that the star is visible to the naked eye under good conditions, though faint. The light arriving from it tonight left the star around the year 1825, roughly the time when Friedrich Bessel was beginning the careful positional measurements that would lead, 13 years later, to the first accurate distance to another star. The light from Methuselah was crossing the space between that star and Earth, while the tools for understanding what stars actually are were still being assembled. The star is older than almost anything else we can observe. The understanding of what it is made of, how it formed, and how old it actually is less than a century old. For most of the time that light has been crossing the space between that star and this planet, no one on this planet had any idea what a star was in physical terms. The observation and the understanding of the observation are separated by an interval that makes the apparent age paradox look modest. What the measurement correction also reveals is something less comfortable than the resolution of a paradox. It reveals that our age estimate for the universe itself carries uncertainties that are large enough to matter when we are dealing with very old objects. 13.8 billion years is a precise-sounding number. The uncertainty on that number, depending on the measurement method used, is somewhere in the range of hundreds of millions of years. Different measurement techniques currently produce values that do not quite agree with each other, a discrepancy that cosmologists are actively working to resolve. The Methuselah star briefly appeared to violate a boundary that may itself not be as precisely located as we had assumed. Both the star's age and the universe's age are estimates built from models built from measurements, and the measurements have errors, and the models have assumptions, and the assumptions are being continuously tested and occasionally revised. The age of the universe is not a number that was read off a dial somewhere. It is an inference, maintained by a community of researchers who keep checking it against new data and adjusting when the data demands it. That process of checking is the thing that makes the number trustworthy, not its precision. A number that has been tested against multiple independent methods and survived, even with acknowledged uncertainties, is more reliable than a precise-sounding number that has never been seriously challenged. The Methuselah star challenged our measurements in a way that turned out to be productive, revealing a systematic error that improved the quality of the tools used to make similar estimates. The star itself is indifferent to all of this. It has been burning hydrogen into helium for 14 billion years and will continue until its fuel runs out, at which point it will expand into a red giant and shed its outer layers. The process is not rushed. For a star of its mass, the timeline extends billions of years further into the future. The crisis it created lasted a few years. The star will outlast the crisis by an interval that makes the crisis invisible. If an age estimate that seemed to violate the boundary of the universe turned out to hinge on a small correction to a distance measurement, what other conclusions we currently hold with confidence are waiting for a similar careful second look? Gravity is the great sculptor of the universe, and it has never once produced a perfect sphere. This is not an oversight. It is a consequence of physics so fundamental that the failure of perfection is, in a precise sense, guaranteed. Any object large enough for gravity to pull into a roughly spherical shape is also large enough for rotation to deform that shape, spin something. And the material at the equator experiences a centrifugal tendency outward. The faster the spin, the stronger that tendency. Gravity pulls inward, rotation pushes outward at the equator, and the result is always a compromise, always a shape that is wider than it is tall, always something that a mathematician would call an oblate spheroid rather than a sphere. The Earth is about 43 kilometers wider at the equator than it is tall from pole to pole. 43 kilometers is roughly the driving distance from Washington, D.C. to Baltimore. The planet you are lying on right now is, by that margin, fatter around the middle than it is from top to bottom, and that asymmetry is the direct result of the roughly 1,600 kilometers per hour at which the equatorial surface moves due to the planet's rotation. You do not feel that speed, but the planet's shape records it, permanently, in the bulge. Saturn is more dramatic. It rotates once every 10.5 hours, fast enough that its equatorial diameter is about 10% larger than its polar diameter. The difference is visible in photographs. Saturn looks noticeably flattened, like a sphere that has been pressed gently from above and below, for a gas giant with no solid surface to hold its shape against the rotational forces. The deformation is larger because there is nothing rigid resisting it. Gravity and rotation negotiate the shape continuously, and the negotiation produces something visibly imperfect. Even neutron stars, the densest objects in the universe, short of black holes, objects where a single teaspoon of material would weigh roughly 4 billion tons on Earth's surface, are not perfect spheres. They rotate, many of them rapidly, and rotation deforms them. The deformation is small, measured in millimeters for objects tens of kilometers across, but it is there. The universe has never managed a perfect sphere, even with the most extreme densities and the most extreme gravitational forces available to it. In the 1960s, a team of physicists and engineers decided to test a prediction Albert Einstein had made about the behavior of space and time near a massive rotating body. The prediction, called frame dragging, held that a massive rotating object like Earth would pull the fabric of space-time along with it as it rotates, the way a spinning ball submerged in honey would drag the honey around with it. Not metaphorically drag it. Actually drag it, in a way that would affect the orientation of a gyroscope placed in orbit around the Earth. To test this, you need a gyroscope. Not an ordinary one, a gyroscope whose spin axis is stable enough that any deviation from its original orientation, after accounting for every other known influence, can be attributed to the frame-dragging effect predicted by the theory. The predicted deviation was tiny, less than 42 thousandths of a degree per year, an angle roughly equivalent to the width of a human hair viewed from about 1.5 kilometers away. Detecting a signal that small requires a gyroscope so precisely made that its imperfections do not introduce noise larger than the signal you are trying to find. The team built 4 gyroscopes, each a sphere of fused quartz about the size of a ping-pong ball, coated in a thin layer of the element niobium. The spheres were polished to be the most perfectly round objects ever manufactured by human hands. The most nearly perfect of the 4 deviated from a true sphere by about 40 atomic diameters across its entire surface. 40 atoms. Across an object 38 millimeters wide, the largest deviation from perfect roundness was 40 atoms tall. If you scaled that sphere up to the size of the Earth, the largest mountain on that scaled-up sphere would be about 2.5 meters high. The mission, called Gravity Probe B, launched in 2004 and collected data for about 17 months before the gyroscopes were switched off. The analysis took years. When the results came in, they confirmed the frame-dragging prediction to within about 19% of the theoretical value, a result complicated by an unexpected electrostatic effect that the team had to work carefully to separate from the signal they were measuring. The geodetic effect, a related prediction about how space-time curvature affects a gyroscope's orientation, was confirmed to within about 0.3% of the predicted value. The mission is not usually described as a complete success. The frame-dragging result, while consistent with the theory, was not as precise as hoped because of the electrostatic complication. Some researchers argue the geodetic result was the more significant confirmation, while others note that better measurements of frame dragging have since been achieved through other methods. The 40-atom spheres, the most perfect objects humans have ever made, produced a result that needed significant qualification. What stays with me about this is not the qualification, it is the attempt. A team spent decades designing and building objects more perfectly spherical than anything the universe produces naturally, and used them to test whether the universe behaves as a set of equations written in the early 20th century said it should. The universe, it turns out, does behave that way. The equations were right, the frame dragging is real, the geodetic effect is real. The fabric of space-time does something in the vicinity of a massive rotating object that a gyroscope can detect, given a gyroscope precise enough to detect it. The imperfection of the result is inseparable from the effort of the attempt. You cannot build a more perfect gyroscope and get a cleaner signal without first understanding why the less perfect gyroscope introduced the noise it did. Every complication that had to be worked around required understanding the physics of that complication well enough to subtract it from the data. The electrostatic effect that complicated the frame-dragging measurement was not in the original error budget. Finding it and characterizing it well enough to account for it was itself a contribution to knowledge. The attempt to achieve perfection produced, as a byproduct, a more detailed understanding of imperfection. Nature refuses the perfect sphere for the same reason that the most perfect sphere humans ever built is still 40 atoms from ideal. Perfection in the sense of zero deviation from a mathematical abstraction is not a physical state. It is a limit that physical systems approach and never reach. The mathematics can describe a perfect sphere exactly. The matter cannot instantiate one. Every real object is a negotiation between competing forces, and negotiations do not produce ideal outcomes. They produce outcomes that are stable enough under the current conditions, that hold together against the forces trying to deform them, that persist long enough to be observed. A raindrop falling through air is not a sphere. The bottom flattens as air resistance pushes up against it. A large raindrop wobbles as it falls, oscillating between shapes, because the surface tension holding it together and the air resistance deforming it reach no stable equilibrium. A human egg cell is not a sphere. It is slightly flattened at one end, where the polar body was extruded during the final stage of its formation. The fertilized egg that eventually becomes a person begins as something that a mathematician would not call a sphere, and every stage of development from that point on moves further from spherical symmetry, not toward it. Life, it turns out, has very little use for perfect spheres. Life needs asymmetry. It needs a top and a bottom, a front and a back, a side that faces the light and a side that does not. The developmental programs that build organisms start by breaking symmetry, by establishing axes and gradients and differences in concentration that tell cells where they are and what to become. A perfect sphere has no axes. It has no privileged directions. It is, in that sense, useless as a starting point for building anything with a function. The universe produces things that are spherical enough for their purposes. Stars are spherical enough that the nuclear reactions in their cores are not significantly affected by the equatorial bulge. Planets are spherical enough that gravity can hold atmospheres against them. Cells are roughly spherical enough to maintain the concentration gradients across their membranes that their chemistry depends on. Close enough is not a failure. It is the actual operating condition of every physical system that has ever existed. The 40-atom deviation in the gravity probe B gyroscopes was not a failure of craftsmanship. It was the boundary of what matter can do when organized by the best methods humans have developed for organizing it. That boundary is real. It is not going to be moved to zero, but it can be pushed further. slowly, by understanding more precisely where the deviations come from and why. That is the actual shape of scientific progress, not the achievement of perfection. The careful, continuous mapping of where perfection fails and what the failure reveals. Right now, the planet you are lying on is bulging at the equator by 43 kilometers, rotating at a speed your body cannot feel, carrying you through space at 30 kilometers per second in its orbit, around a sun that is itself moving at 230 kilometers per second, around the center of a galaxy that is falling toward a structure called the Great Attractor at roughly 600 kilometers per second. None of those motions is circular. All of them are approximate. All of them are negotiated outcomes of competing forces that reached a stable enough compromise to persist long enough for you to be lying here thinking about them. The universe, it turns out, runs entirely on close enough, which raises the question of what happens when close enough breaks down, when the negotiation between competing forces stops producing a stable outcome and the compromise collapses. If the universe has never produced a perfect sphere and never will, what does that tell us about the nature of the time those imperfect objects move through? For most of human history, every town kept its own time. Noon was when the sun reached its highest point in the sky above that specific location. A town 30 kilometers to the west experienced noon about 2 minutes later than the town to the east, because the sun reaches its peak at different moments along any east-west line. This was not a problem. Towns were far enough apart and travel slow enough that the difference never mattered. A clock in Bristol running 2 minutes behind a clock in London was not a source of confusion because no one was moving between those cities fast enough for 2 minutes to be significant. Then the railways arrived, and 2 minutes became a problem. A train running on Bristol time, arriving at a station operating on London time, would be simultaneously on schedule by one clock and late by another. Passengers would miss connections. Timetables would be internally inconsistent. The railway companies resolved this by imposing a single standard time across their networks, which meant that for the first time in history, time was not a local phenomenon derived from the position of the sun. It was a distributed agreement, enforced by telegraph, maintained by a signal sent from a single reference point and propagated outward to every station on the network. The reference point was the Royal Observatory at Greenwich, southeast of London. From the 1850s onward, a time signal was transmitted by telegraph wire from Greenwich to railway stations, port authorities, and eventually to a network of clock towers across Britain that would physically drop a ball at a precise moment each day so that ships in harbor could set their chronometers. The time you experience as a natural feature of the world, as something that simply exists and flows uniformly around you, was standardized within the last 2 centuries by a cable running under London and the political decision of a railway company. Time is not uniform. It does not flow at the same rate everywhere. It never did. The equations governing this were worked out in the early 20th century. A clock in stronger gravity runs slower than a clock in weaker gravity. A clock moving faster runs slower than a clock moving more slowly. These are not instrumental errors or philosophical positions. They are measurable physical effects that have been confirmed by direct experiment and that require active correction in any system precise enough to be affected by them. The network of satellites providing positioning data to phones and navigation systems around the world carries atomic clocks accurate to about 1 second in 300 million years. Those clocks run in weaker gravity than clocks on the surface, which means they run slightly faster than a surface clock by about 45 microseconds per day. They also move fast enough in orbit that relativistic time dilation slows them by about 7 microseconds per day relative to a surface clock. The net effect is that the satellite clocks gain about 38 microseconds per day relative to ground-based receivers. 38 microseconds. That sounds negligible. At the speed of light, 38 microseconds corresponds to about 11 kilometers of positional error. Accumulated over a day without correction, a navigation system would drift by roughly 11 kilometers. Over a week, it would be off by more than 70 kilometers. The correction is applied continuously, automatically, because without it, the system stops working. Every time a phone calculates a location, it is implicitly accounting for the fact that time runs at different rates depending on where you are and how fast you are moving. General and special relativity are not abstract theories confined to thought experiments. They are the operating assumptions of infrastructure that billions of people use daily without knowing it. What Einstein's equations describe is not a correction to time. They describe what time actually is. Time is not a background against which events occur. It is a dimension of space-time that responds to mass and motion, that stretches and compresses in ways that are physically real and measurable. The Greenwich cable standardized a human agreement about time. The physics underneath that agreement is under no obligation to honor it. Two events that are simultaneous for one observer are not simultaneous for an observer moving relative to the first. This is not a statement about perception or measurement error. It is a statement about the structure of space-time. Simultaneity is not a universal property of events. It is a property of events relative to a reference frame. There is no single answer to the question of whether two events happened at the same time, only answers relative to specific states of motion. The practical consequences of this are small at the speeds humans ordinarily move, but the conceptual consequence is not small at all. The present moment, the sense you have right now of everything existing simultaneously in a shared now, is a local phenomenon. An observer moving relative to you at a significant fraction of the speed of light would not share your now. They would have a now that includes some of your past and some of your future, arranged differently than yours. Neither of you would be wrong. You would each be accurately reporting the structure of space-time from your reference frame, and those reports would not be reconcilable into a single universal present. The thing that stops me about this is not the mathematics. It is the implication for the experience of being alive at a specific moment. The feeling that there is a now, that the present is special and distinct from past and future, is one of the most immediate and unquestionable features of conscious experience. And the physics says that this feature, however real it feels, is not a feature of the universe. It is a feature of your location and your velocity. It is, in a precise sense, local. This does not mean the present is not real. It means that the present is not shared in the way that experience suggests. Every person, every object, every point in space-time has its own local present, its own local flow of time, determined by its own history of motion and gravitational exposure. The universe does not have a single clock. It never did. The Greenwich cable was a human attempt to impose one. What the physics reveals is that the universe was never going to cooperate with that attempt beyond the precision levels at which the difference is too small to matter. Clocks on the surface of Earth, corrected to a common standard and synchronized by signals traveling at the speed of light, agree with each other to better than 1 microsecond. That level of agreement is genuinely impressive and genuinely useful. It is also an approximation. At the level of 1 nanosecond, clocks on different sides of a building disagree because they sit at slightly different heights in Earth's gravitational field and therefore experience time at slightly different rates. At the level of 1 picosecond, the floor of the room you are lying in runs on different time than the ceiling. The difference is unmeasurably small in practical terms. In physical terms, it is real. There is something in all of this that does not resolve into either comfort or alarm, and I want to be honest about that rather than smooth it over. The physics says that time is local, that simultaneity is frame-dependent, that there is no universal present. The experience of being alive says that right now, in this room, something is happening, and that it is happening now, and that now feels categorically different from before and after. Both of these things are true, and they do not fully reconcile. The physics describes the structure of space-time. The experience describes something about consciousness that the physics has not yet fully accounted for. The gap between those two descriptions is not currently closed. What is closed, or at least much better understood than it was, is the question of what time does near very large masses moving very quickly. It slows, measurably, predictably, correctable for. The GPS system runs because the people who built it understood this and built the correction in. The universe is indifferent to whether the correction is built in or not. Time does what it does regardless of whether any instrument is precise enough to notice. Right now, the time flowing for you in this room is running at a rate determined by your height above Earth's center and your velocity relative to the satellite clocks overhead. The difference from what a hypothetical clock at sea level at rest would show is smaller than any biological system could detect. Your nervous system does not have nanosecond resolution. Your experience of now is orders of magnitude coarser than the level at which relativistic effects become significant for you personally. You will not feel the difference. The difference is there regardless. The Greenwich cable ran from the observatory to the city and eventually to the coast. It carried a signal that said, "This is now. Calibrate to this. Use this as the reference." The universe does not have a cable running from anywhere to anywhere. It has 400 billion stars in this galaxy alone, each with its own local time, each running slightly differently from every other. None of them wrong, all of them accurate descriptions of what time is doing at that specific location in space-time. The agreement is ours. The physics underneath it belongs to something much older and much less interested in agreement. If time itself is local, running differently depending on where you are and how fast you are moving, what does that imply about the nature of the choices made within it? There is a wasp about 2 centimeters long that does something no human surgeon has ever replicated with instruments. It finds a cockroach. It stings it twice. The first sting targets the midsection, delivering a temporary paralysis to the front legs that lasts long enough for the wasp to prepare the second sting with precision. The second sting goes directly into the cockroach's head, into a region of neural tissue called the subesophageal ganglion, with an accuracy that researchers have confirmed targets specific neural circuitry. Not nearby, not approximately, the specific cluster of neurons that governs the escape reflex. After the second sting, the cockroach does not die. It does not become paralyzed. It grooms itself, moves around, responds to touch. Every system is running. The cockroach is, by most biological measures, intact and functional. Except that it will not run away. The specific neural pathway that generates the impulse to escape from threat has been chemically suppressed. The cockroach sits where it is, passive, while the wasp chews off half its antennae, drinks the fluid that leaks out, and then leads the cockroach by the remaining antenna stub into a burrow, where it lays an egg on the cockroach's abdomen, seals the burrow, and leaves. The cockroach waits in the dark, alive, grooming, not leaving. The wasp larva hatches and consumes the cockroach from the outside in, keeping it alive as long as possible by avoiding the vital organs until the end. The cockroach, throughout this process, has the physical capacity to move. Its legs work. Its nervous system is intact except for that one suppressed pathway. It simply does not initiate escape. The neurotransmitter the wasp injected has seen to that. The emerald jewel wasp, which is what this animal is called, did not learn this technique. It did not develop it through trial and error within its own lifetime. It was born knowing where to sting, because every ancestor that stung incorrectly left fewer offspring than every ancestor that stung correctly, and over millions of generations that differential reproductive success encoded the precision into the genome. The wasp is running a behavioral program refined across timescales that make human civilization look like a rounding error. Now consider a single-celled organism called Toxoplasma gondii. It is a parasite with a complicated life cycle that involves, at its most productive stage, the gut of a cat. Toxoplasma reproduces sexually only inside cat intestines. To get there, it has to travel through an intermediate host, most commonly a rodent. When it infects a rat or a mouse, something changes in the rodent's behavior that has been the subject of sustained scientific attention for decades. Infected rodents show reduced fear responses specifically to cat odor. Some studies report that infected rodents are not merely less afraid of cat scent, but actually show something that looks, in behavioral terms, like attraction to it. They approach areas marked with cat urine rather than avoiding them. The mechanism appears to involve the parasite encysting in neural tissue, including regions of the brain involved in fear processing and reward, and altering the local neurochemistry in ways that specifically affect responses to cat-related stimuli while leaving most other behaviors intact. The parasite is not making the rodent generally reckless. It is making the rodent specifically less averse to the one thing that would get it eaten by the one animal the parasite needs to complete its reproductive cycle. The precision of that targeting, achieved by an organism with no nervous system of its own, is the part that takes a moment to absorb fully. Toxoplasma also infects humans. Estimates of the proportion of the global human population carrying latent toxoplasma infections range from roughly 20% to over 50%, depending on geography and methodology, with higher rates in some regions of Europe and Latin America. In most people with healthy immune systems, the infection produces no symptoms and is effectively invisible. The organism encysts in tissue, including brain tissue, and sits there dormant, detectable only through blood tests. Whether it does anything to human behavior is a question that has generated a significant body of research and a significant amount of disagreement about what that research actually shows. Some studies report correlations between toxoplasma infection and various behavioral and personality measures. Others report no significant effects or question the methodology of studies that do. The honest summary is that there are enough replicated findings to take the question seriously and not enough to draw firm conclusions about what, if anything, a latent toxoplasma infection actually does to a human being. I want to be careful here about the difference between what is established and what is suggested, because the question is genuinely important and genuinely unsettled. What is established is that toxoplasma alters rodent behavior through direct neural intervention in ways that serve the parasite's reproductive interests. What is suggested by some human studies is that the parasite may have measurable effects on human psychology. What is not established is the mechanism, the magnitude, or the causal direction of any human behavioral effects. Correlation in observational studies is not the same as the targeted neural intervention documented in rodents. But the question the wasp and the parasite together raise does not require the human data to be resolved to be worth taking seriously. The question is this: what is the boundary between a behavior that is yours and a behavior that is running in you? The cockroach has a nervous system. It has behavioral repertoires. Under normal circumstances, it initiates escape from threat. That initiation is, in some sense, the cockroach expressing its own behavioral tendencies. After the wasp's intervention, the escape initiation is suppressed. The cockroach is no longer fully expressing its own behavioral tendencies. Something else is determining what it does. The cockroach cannot tell the difference from the inside, because the part of its neural system that would generate the impulse to leave is the part that has been silenced. This is not a question confined to cockroaches and wasps. It is a question about every nervous system, including yours. The behaviors you experience as chosen emerge from neural systems shaped by genetics, by developmental environment, by every experience your nervous system has undergone since before you were born, by the neurochemical state of your brain at this specific moment, which is itself a product of what you have eaten, how much you have slept, what has happened to you today, and the activity of whatever microorganisms currently inhabit your gut and potentially your neural tissue. The experience of choosing feels like something originating from a central, autonomous self. The neuroscience of what is actually happening when a decision is generated looks considerably more distributed, more influenced by prior states, and less centrally authored than the experience suggests. This is not a new observation. Philosophers have been arguing about free will and determinism for as long as there have been philosophers. What the emerald jewel wasp and Toxoplasma gondii add to that argument is not a resolution but a precision. They demonstrate that behavioral control can be exerted from outside a nervous system with enough specificity to alter particular behaviors while leaving others intact, and that the organism being controlled cannot detect the intervention from the inside. The cockroach does not feel controlled. It feels, insofar as it feels anything, like itself. How you would know if something analogous were true of you. Not necessarily a parasite, not necessarily any external agent at all. The influences that shape neural systems are numerous, continuous, and mostly below the threshold of awareness. The sense of being the author of your own behavior is itself a product of neural systems that can be altered, that have been altered throughout your life, that are being altered right now by the simple fact of lying still in the dark with your nervous system running at lower arousal than it was an hour ago. I have spent more time than I expected thinking about the cockroach. Not because its situation is identical to ours. It is not. But because the specificity of what the wasp does, the targeting of one pathway while leaving the rest intact, describes a principle that seems to generalize. Behavior is modular in ways that experience does not reveal. You can alter specific behavioral tendencies while leaving most of the system functional and while leaving the subjective sense of normalcy undisturbed. The organism continues to experience itself as itself. The alteration is invisible from the inside. What grounds the experience of being a self, of having a continuous identity that persists through time and authors its own choices, if that experience cannot reliably detect the influences that are shaping it? That question has no clean answer in neuroscience, in philosophy, or in the behavioral ecology of parasitic wasps. It sits open. If the boundary between your behavior and behavior running in you is not as clear as experience suggests, what does that imply about the self that believes it is crossing a black hole's event horizon, watching the universe outside, thinking it understands what is happening to it? Somewhere near the center of this galaxy, about 26,000 light-years from the room you are lying in, there is a region of space where the rules that govern every other physical process in the observable universe begin to fail. Not approximately fail. Not fail in ways that can be corrected with better instruments. Fail in the sense that the equations describing what happens there produce outputs that are not numbers in any useful sense. The mathematics arrives at a point and stops. The object at the center of that region has a mass roughly 4 million times that of the Sun. If you replace the Sun with that object, its gravitational influence on the outer planets would be identical to what it is now. Pluto would continue its slow orbit undisturbed. The difference would be felt only within a region called the event horizon, a boundary not made of matter, not marked by any physical surface, but defined entirely by the fact that beyond it, the escape velocity exceeds the speed of light. Cross it, and the direction toward the singularity becomes, in a precise geometric sense, the direction of the future. You cannot avoid it any more than you can avoid tomorrow. Stars wander too close to this region occasionally. When one does, what happens to it has a name that sounds almost playful for what it describes. Spaghettification. The term refers to the tidal stretching that occurs when an object enters a region where the difference in gravitational pull between its near side and its far side becomes large enough to overcome the forces holding the object together. For a star, this happens well outside the event horizon, in the region where the tidal gradient is steep enough to exceed the star's self-gravity. The near side of the star is pulled more strongly than the center, and the center more strongly than the far side. The star stretches along the radial direction, compresses perpendicular to it, and is drawn out into a long, thin stream of plasma that spirals inward. The stream does not disappear cleanly. About half of the disrupted stellar material is captured into a tight orbit and forms an accretion disk, a swirling structure of superheated plasma that radiates enormous amounts of energy as it gradually spirals inward. The other half is flung outward at high velocity, escaping the system entirely. A star that existed as a coherent object for millions or billions of years is redistributed across these two fates in a matter of weeks. Some of it falls in, some of it escapes. The identity of the star, as a bounded, self-sustaining nuclear furnace with a particular mass and composition and luminosity, ceases to exist. What remains is the question that theoretical physics has been sitting with for decades and is not yet fully answered. Information, in the technical sense used by physicists, is not the same as meaning. Information is a measure of the distinguishability of states. Two configurations of matter are informationally distinct if there is in principle some observation that could tell them apart. The laws of physics, as currently understood, outside of black holes, are informationally conservative. The total information content of a closed system is preserved, even as the system evolves. Burn a book, and the information encoded in its text is not destroyed. It is redistributed, in principle, recoverable from the precise positions and velocities of every molecule of smoke and ash and heat, even though in practice no one could ever perform that reconstruction. The information is there, scrambled, but present. Black holes appear to violate this. The argument runs as follows. Whatever falls past an event horizon is, from the perspective of the outside universe, causally disconnected from everything beyond it. No signal, no particle, no influence of any kind can travel from inside the horizon to outside. If information about the infalling matter is carried past the horizon and cannot return, and if the black hole eventually evaporates through a process of thermal radiation, then the information that fell in is simply gone, not scrambled, not recoverable in principle, gone. This is called the black hole information paradox, and it is not a minor technical quibble. If information can be destroyed, one of the foundational principles of quantum mechanics is violated. The two most successful frameworks in the history of physics, general relativity and quantum mechanics, make predictions about black holes that cannot both be true. One of them must be incomplete in a way that has not yet been identified. Stephen Hawking spent roughly 2 decades maintaining that information was genuinely destroyed, that black holes represented a true exception to the conservation of information. In 2004, he changed his position publicly, conceding that the information was likely preserved somehow, though the mechanism remained unclear. The problem has not been solved. Various proposals exist, among them the idea that information is encoded in subtle correlations in the thermal radiation the black hole emits, or that it escapes through some form of quantum entanglement between the interior and the exterior that general relativity does not account for. None of these proposals has been confirmed. The paradox remains open. What the paradox is actually asking, underneath the technical language, is whether identity is conserved. A star that falls into a black hole had a specific configuration of matter and energy. That configuration encoded its history, its composition, its current state. If the information describing that configuration is preserved through the black hole's eventual evaporation, then, in some formal sense, the star's identity persists, scrambled beyond any practical recovery but present in the correlations of the outgoing radiation. If the information is destroyed, the star's identity is not scrambled, it is erased. There is no sense in which the outgoing radiation remembers it. The question matters beyond stars. You are a configuration of matter and energy. The atoms in your body are arranged in a particular way that has never existed before and will never exist again in exactly this form. That arrangement encodes your physical history in ways that are not fully legible even to the best available instruments, but that are, in principle, there. The question of whether information is conserved in black holes is in part a question about whether the universe keeps records. Whether the specific configuration of matter that constitutes a particular thing, a star, a cell, a person, persists in any form after the configuration is disrupted, or whether disruption of sufficient severity constitutes a true ending, a state from which nothing carries forward. Physics currently leans toward preservation. The arguments for information conservation have become more detailed and technically sophisticated over the past 2 decades, and most working physicists now believe that information is not destroyed in black holes, even if no one has demonstrated precisely how it escapes. But the mechanism is not understood, and the belief, however well supported by theoretical arguments, rests on a foundation that has not been directly tested. There is an additional strangeness that the geometry of black holes introduces, and it concerns time rather than information. An observer falling toward a black hole, from their own perspective, crosses the event horizon without any local drama. There is no wall, no flash of light, no physical surface to collide with. The event horizon is a mathematical boundary, defined by causal structure, and it is invisible to a freely falling observer. From the inside, looking outward, everything initially appears normal. The infalling observer looks back and sees the universe outside, though progressively redshifted and distorted by the geometry they are moving through. From the outside, something different occurs. An observer watching someone fall toward a black hole sees the infalling figure slow as they approach the horizon, their signals becoming increasingly redshifted. Their image freezing and fading as the light they emit takes progressively longer to climb out of the deepening gravitational well. To the outside observer, the infalling figure never crosses the horizon. They asymptotically approach it, frozen in time, for as long as the black hole exists. Both descriptions are accurate. Both describe what is physically happening, from their respective reference frames. The infalling observer crosses the horizon and eventually reaches the singularity. The outside observer sees the infalling figure freeze at the horizon indefinitely. These two accounts of the same event cannot be reconciled into a single narrative without a framework that does not yet exist. General relativity describes the geometry. It does not resolve the tension between what the two observers experience. The question of what happens to information, to identity, to the specific configuration of matter that constitutes a particular thing when that thing encounters sufficient disruption, is not resolved by current physics. The equations describe the geometry of what happens near a black hole with extraordinary precision. They do not answer the question of what it means for a configuration to persist or cease. The singularity at the center is where the description runs out. The mathematics produces a point of infinite density, which is the physics telling you that the theory being applied is no longer adequate, not that an actual infinity exists. Something happens at the singularity. The available frameworks cannot describe it. What comes after, if anything comes after, is not something current physics can speak to. The star that was spaghettified was, before it encountered the tidal gradient, a self-sustaining process. Nuclear fusion, its core, radiation pressure balancing gravity, a particular spectrum of light emerging from its surface. That process ran for millions of years and then ended. The matter that composed it continues. Some of it is in the accretion disk, radiating. Some escaped into interstellar space. The process is over. The matter is not. Whether that distinction between the continuation of matter and the cessation of the process that organized it is a meaningful one, or whether it only appears meaningful to nervous systems that have a stake in the answer, is a question the physics does not settle. It only tells you where the description stops. If the information describing a configuration of matter is preserved through a black hole's evaporation but unrecoverable in practice, in what sense does preservation matter? In November of 1967, a graduate student at Cambridge was working through paper chart recordings of radio signals from the sky, looking for a particular kind of flickering that might indicate a compact radio source. The work was not glamorous. The charts were produced by a radio telescope she had helped build by hand, stringing wire across nearly 2 hectares of English countryside. Reading them required patience and a tolerance for ambiguity, because most of what a radio telescope picks up is noise, local interference, signals from human technology bouncing off the ionosphere, and the steady background hiss of the cosmos itself. The skill was in knowing what to ignore and what to pursue. Jocelyn Bell noticed something she called scruff. It was a small irregularity in the signal, a patch of the recording that did not look like the smooth, slow variations she was expecting from distant radio sources. It recurred. Same patch of sky, same kind of signal, appearing each time that region rotated into the telescope's view. She flagged it and kept watching. When the team set up equipment to record the signal at higher time resolution, what came back was a pulse. A single, sharp pulse, repeating with a period of 1.3373 seconds. Then another. Then another. Perfectly spaced, perfectly regular. A clock ticking in the sky at a precision that no natural process they could immediately think of was known to produce. The team considered the possibility that it was artificial. The notes from that period include the label LGM1, Little Green Men. It was not entirely a joke. The signal was too regular to be easily explained as a natural phenomenon with the frameworks available at the time. Naturally occurring processes that produce periodic signals, rotating planets, orbiting binary stars, tend to have periods of hours or days, not fractions of a second. A period of 1.3373 seconds, maintained with a stability that later analysis showed was accurate to better than 1 part in 10 billion per day, was outside the range of what most natural mechanisms were known to produce. The team did not publish immediately. They kept checking. They looked for a Doppler shift that would indicate the source was orbiting a planet, which would have supported the artificial origin hypothesis. They found none. They found 3 more pulsing sources in other parts of the sky. Whatever this was, it was not a single anomaly. It was a class of objects. The explanation, when it came together, required pulling from theoretical work that had been done years earlier and largely set aside. In the 1930s, 2 astronomers had proposed that when a massive star exhausts its fuel and collapses, the core might compress to such extreme density that the electrons and protons are forced together into neutrons. The resulting object would be roughly 20 kilometers across, containing more mass than the Sun, spinning rapidly because the collapse conserves angular momentum, the way a figure skater spins faster when pulling in their arms, and generating intense magnetic fields that would beam radio emission from the magnetic poles. If those beams swept across Earth as the neutron star rotated, a distant observer would receive a pulse each time the beam swept by. A neutron star, 20 kilometers across, more mass than the Sun. If you replaced Earth with a neutron star of the same mass, the object would fit comfortably inside a city, with a surface gravity roughly 200 billion times stronger than what you are lying against right now. A cubic centimeter of its material, a cube about the size of a sugar cube, would weigh roughly 400 million tons. The number is almost impossible to carry in the mind without it slipping into abstraction, so consider it this way. That sugar cube, placed on one side of a scale, would outweigh every aircraft carrier the United States has ever built, combined, by a factor of roughly 1,000. And this object, this collapsed remnant of a dead star, was rotating 30 times per second when Bell first detected it, maintaining a clock precision that exceeded the best atomic clocks available on Earth at the time of its discovery. The Nobel Prize in Physics for 1974 was awarded for the discovery of pulsars. It went to Anthony Hewish, Bell's supervisor, and to Martin Ryle, who had contributed to radio astronomy methodology. Jocelyn Bell, who noticed the scruff, who flagged the irregularity, who stayed with it when it would have been reasonable to dismiss it as interference, was not included. The exclusion was noted at the time and has been discussed in the decades since. Hewish defended the decision on the grounds that Bell was a graduate student working within a program he had designed. Others in the field disagreed publicly. Bell herself has addressed it in interviews over the years with a composure that strikes me as more considered than the institutions involved deserve credit for prompting. She has said that she was not resentful, that the work mattered more than the recognition, and that she has spent her career trying to ensure that students who find important things get credit for finding them. What she found has not stopped being useful. Pulsars are now among the most precisely characterized objects in astrophysics. Millisecond pulsars, a class that rotates hundreds of times per second, are stable enough that arrays of them distributed across the sky can be used as a galactic-scale detector for gravitational waves, ripples in space-time produced by massive objects accelerating. The principle is that a gravitational wave passing between Earth and a pulsar would stretch or compress the space between them by a tiny amount, causing the pulse arrival times to shift by a correspondingly tiny amount. By monitoring many pulsars simultaneously and looking for correlated timing variations, it becomes possible to detect gravitational waves with wavelengths measured in light years, far longer than any ground-based detector can reach. The scruff in a graduate student's chart recording in 1967 is now part of the infrastructure for detecting ripples in the fabric of space-time. The signal was always there. The pulsars have been rotating and beaming radio emission for millions of years, some of them for longer than the Earth has existed in its current form. The one Bell detected, now catalogued as PSRB 1919+21, has been ticking at 1.3373 seconds per rotation since long before any instrument existed to receive it. The signal was arriving at Earth, undetected, for all of that time. What changed in November of 1967 was not the signal. It was the presence of someone paying close enough attention to notice that something small did not fit. That is a particular kind of attention. It is not the attention of someone scanning for expected results. It is the attention of someone who has looked at enough data to recognize when something departs from the texture of everything around it, and who does not immediately reach for the explanation that would allow them to keep moving. Bell kept a handwritten note of the anomaly. She returned to it. She escalated it carefully. She was 24 years old and working on a doctoral thesis, and she treated the thing that did not fit as the most important thing in the data because it was. The institutions that surrounded her did not recognize this at the same speed she did. That is a different kind of record, less flattering, also worth keeping. Millisecond pulsars have now been timed with enough precision that their arrival time residuals, the tiny differences between predicted and actual pulse arrival times, are measured in nanoseconds. 1 nanosecond is 1/1000th of a second. If you divided a single second into 1 billion equal parts, each part would be a nanosecond. The timing stability required to detect gravitational waves using pulsar arrays involves tracking deviations at that level, across baselines of thousands of light years, sustained over years of observation. The most stable clocks in the observable universe are the corpses of stars. They do not keep time deliberately. They keep time because the physics of rotating, magnetized neutron stars does not have any mechanism for introducing significant variation. Angular momentum is conserved. The magnetic field is locked in. The beam sweeps around with the rotation. Variation enters only through the slow loss of rotational energy to the emitted radiation, which causes an extremely gradual lengthening of the period over millions of years, predictable enough to correct for. The clock does not try to be precise. It is precise because the physics leaves no room for imprecision. There is a contrast here with the clocks humans build. which require continuous engineering effort to approach a stability that rotating neutron stars achieve as a consequence of simply being what they are. The atomic clocks in GPS satellites, accurate to 1 second in 300 million years, are remarkable achievements of applied physics and precision engineering. They are also less stable over long baselines than the best millisecond pulsars. The natural object, produced by the death of a star, runs more accurately than the most careful human construction. Not because stars are trying to be clocks, because the physics of their remnants has no room for the errors that engineering must work to suppress. Bell noticed the scruff in November. The paper was published in February of 1968. The Nobel was awarded in '74. The pulsar timing arrays that use Bell's discovery as part of gravitational wave detection came decades after that. The full arc of what that one anomaly, that one patch of irregular recording on a paper chart, has contributed to physics is still being extended. The signal arrived long before anyone was positioned to receive it. The receiving required someone who had built the instrument, learned to read its output, and refused to dismiss what did not fit. If the most precise natural clocks in the universe are the remnants of stellar deaths, and the most energetic particles ever detected arrive from sources we have not yet identified, what does the gap between those two facts tell us about what we are still not positioned to receive? On the 15th of October, 1991, a detector array spread across the Utah desert recorded something that the physicists analyzing the data initially assumed was an equipment malfunction. The array was called the Fly's Eye detector, named for its design, a collection of mirrors and photomultiplier tubes that watch the night sky the way a compound eye watches its surroundings, each unit covering a different patch of sky, the whole system sensitive to the faint fluorescent glow that high-energy particles produce when they slam into the upper atmosphere and cascade downward in a shower of secondary particles. The array had been running for years. It had seen a lot. What it recorded that night was a cosmic ray with an energy of approximately 3 × 10 to the 20th power electron volts. That number needs a translation before it means anything. A single electron volt is the energy gained by one electron accelerating through an electric potential difference of 1 volt. It is an extraordinarily small unit of energy, appropriate for describing individual subatomic processes. The particle detected over Utah that night carried 3 × 10 to the 20th of them. If you wanted to express that energy in more familiar terms, it is roughly equivalent to the kinetic energy of a baseball thrown by a professional pitcher. 90 miles per hour. A few hundred grams of mass moving at that speed. That energy, concentrated into a single subatomic particle, a proton, something with a mass roughly 1,800 times smaller than a single atom of hydrogen. The physicists called it the "oh my God" particle. The name was informal, used in conversation before the formal designation was assigned, and it captured something genuine about what the data showed, not performed astonishment. The actual response of people who had spent careers working with high-energy cosmic rays and had never seen anything close to this. The problem the particle presented was not just its energy, it was its energy in the context of a constraint that physics had established 25 years earlier. In 1966, 3 physicists working independently arrived at the same conclusion about the maximum energy a cosmic ray proton could carry over cosmological distances. The reasoning runs like this: the universe is filled with photons left over from the early universe, the same background radiation that Bell's pulsars helped calibrate. These photons have very low energy individually, but there are a lot of them. Roughly 411 per cubic centimeter of space everywhere in the observable universe. A proton moving fast enough will interact with these photons, and above a certain energy threshold the interaction becomes inelastic, meaning energy is lost from the proton into the production of new particles. The proton bleeds energy with every interaction, and the interactions are frequent enough that above roughly 5 times 10 to the 19th electron volts, a proton traveling more than about 160 million light-years loses so much energy it should drop below the threshold. The oh my god particle had energy well above that threshold, which means one of several things must be true. The particle traveled less than roughly 160 million light-years, which means its source is somewhere in the relatively local universe and should be identifiable. Or, the particle is not a proton but something heavier that interacts differently with the background photons. Or the physics describing those interactions is incomplete in some way that has not yet been identified. Or the measurement itself was wrong. The measurement was checked carefully. The fly's eye data was analyzed multiple times. Other detectors subsequently recorded particles in the same energy range, not as extreme as the October 1991 event, but close enough to confirm that the phenomenon was real and not an instrumental artifact. The oh my god particle is not unique. It is the most extreme confirmed example of a class of ultra-high energy cosmic rays that should not be arriving at Earth with the energies they carry, given what physics predicts about how far they could have traveled. The source has not been identified. The candidates are not modest objects. To accelerate a proton to that energy requires a mechanism capable of sustaining electric fields or shock fronts across enormous distances with enormous power. Active galactic nuclei, the extremely bright cores of galaxies where supermassive black holes are actively consuming material and driving powerful jets of plasma outward at near light speed, are among the leading candidates. Gamma-ray bursts, the most energetic explosive events in the observable universe, are another. Some proposals involve more exotic physics, processes that operate differently at the highest energies than current frameworks predict. Consider what it means to say a proton was traveling at that speed. Light travels at approximately 300,000 kilometers per second in vacuum. Nothing with mass can reach that speed, but there is no limit, in principle, on how close to that speed something with mass can get, provided enough energy is available to accelerate it. The oh my god particle was moving at a speed so close to the speed of light that if you placed it in a race with a photon, both starting from the Andromeda galaxy 2.5 million light-years away, the photon would arrive at Earth first by roughly the time it takes a human heart to complete one beat. One beat across 2.5 million light-years of travel. At that speed, the particle's own experience of time, if it had one, would be radically compressed relative to ours. A proton traveling from a source 100 million light-years away at that velocity would, in its own reference frame, experience the journey as lasting a tiny fraction of a second. From our reference frame, the journey took 100 million years. Both are accurate descriptions of what happened, from their respective frames. The particle arrived here carrying energy from an event that, by our reckoning, occurred before the ancestors of our species existed. That is not a metaphor for deep time. It is a description of what the data implies about the provenance of a single subatomic particle that hit the atmosphere over Utah on an October night in 1991. The atmosphere absorbed it, of course. The proton, or whatever it was, never reached the ground. It collided with a nucleus in the upper atmosphere at roughly 60 kilometers altitude and produced a cascade of secondary particles, a shower spreading outward in a cone tens of kilometers wide by the time it reached ground level. The fly's eye detected the faint ultraviolet glow the shower produced as it ionized air molecules on its way down. The original particle was gone within microseconds of entering the atmosphere. What remained was the energy it deposited, spread across an enormous volume of air, slowly dissipating into heat. This is what detection means at this scale. You do not catch the particle. You read the trace it left in a medium it destroyed itself passing through, reconstruct the properties of the original from the geometry and intensity of the secondary shower, and work backward to an energy estimate that carries uncertainties of its own. The oh my god particle's energy is an inference from a shadow, not a direct measurement. The inference is well supported and has been analyzed carefully. But it is worth being precise about what was actually observed and what was calculated from the observation. The gap between observation and inference is not a weakness of the measurement. It is the condition under which physics operates at the frontier. You never see the thing directly. You see what it does to something else, and you reason carefully from there. Bell saw what a pulsar did to her chart recordings. Bessel saw what a nearby star did to its apparent position against a background of more distant stars. The fly's eye saw what an ultra-high energy particle did to a column of atmosphere 60 kilometers up. The thing itself was always somewhere else, gone by the time the evidence reached the instrument. Physics at every scale works this way. You are never in direct contact with the phenomenon. You are always reading evidence, always working from traces, always reasoning backward from effect to cause. The universe does not present itself for direct inspection. It leaves marks, and you learn to read them. The quality of the reading depends on the quality of the attention brought to it, and on the quality of the frameworks used to interpret what the attention finds. The oh my God particle left a very clear mark. Where it came from, what produced it, how it reached the energy it carried, remain open. The particle arrived with a message encoded in its energy and its trajectory, and we have not yet developed the framework to read it fully. The array that detected it was decommissioned in 1993. Its successor experiments, larger and more sensitive, have continued cataloging ultra-high energy cosmic rays. The source of the most energetic ones remains unconfirmed. Every candidate involves physics operating at scales and energies far beyond anything reproducible in a laboratory. Whatever is out there accelerating particles to these energies is doing something that our current frameworks describe only approximately, and only from the outside. Something in the universe is capable of this. We do not know what. We know it because the evidence arrived in Utah, briefly lit up a column of atmosphere, and was gone. If the most energetic particle ever detected carries a message from a source we have not identified, and if detecting it required an instrument watching the sky on exactly the right night, in exactly the right direction, how many messages of that kind have already arrived and dissolved into air before any instrument existed to receive them? The largest structure in the observable universe is not a galaxy. It is not a cluster of galaxies, not the filaments of hot gas stretching between clusters, not any arrangement of matter that glows or radiates or can be detected by any instrument sensitive to light. The largest structure is an absence. A region of space roughly 330 million light-years across, containing almost none of the matter that fills the rest of the observable universe. 330 million light-years. If you drove at highway speed without stopping, covering that distance would take roughly 3.5 quadrillion years. The current age of the universe is 13.8 billion years. You would need to drive for about 250,000 times the current age of the universe to cross it, and that is the size of an empty region. A hole in the distribution of galaxies so large that when astronomers first mapped it in the late 1970s and confirmed it through the 1980s, some of them spent time checking whether the survey instruments had a systematic bias that might be creating a false gap in the data. The Boötes Void, named for the constellation in whose direction it lies, is not completely empty. There are a small number of galaxies within it, roughly 60 confirmed at the time of the most recent detailed surveys, scattered through a volume that, at average cosmic density, should contain something closer to 2,000. It is not a true vacuum. It is a severe underdensity, a region where the gravitational processes that usually pull matter into filaments and clusters and walls have left almost nothing behind. The question of how it formed is connected to something fundamental about the way the universe is structured at the largest scales. When the universe was young, the distribution of matter was not perfectly smooth. The quantum fluctuations that inflation stretched to cosmic scales left slight variations in density. Regions marginally denser than average, and regions marginally less dense. Over billions of years, gravity amplified those variations. The denser regions attracted more matter, grew denser still, eventually collapsing into the filaments and sheets and clusters that make up what cosmologists call the cosmic web. The less dense regions lost matter to their surroundings, grew emptier, became voids. What you see in the large-scale structure of the universe today is the quantum noise of the first fraction of a second, written across 300 million light-years of space in the language of galaxy distribution. The cosmic web is the term for the overall structure that this process produced. Viewed at large enough scales, the universe looks like a sponge, or more precisely, like the foam that forms on the surface of a liquid being agitated. Dense filaments of matter, each one containing thousands of galaxies, intersect at nodes where the largest galaxy clusters sit. Between the filaments are the voids, vast regions of relative emptiness that make up most of the volume of the observable universe. Most of the volume. If you took the observable universe, everything within roughly 46 billion light-years of Earth, and divided it into regions, the voids would account for somewhere between 70 and 80% of the total volume. The filaments and walls and clusters, the parts that contain essentially all of the stars, all of the galaxies, all of the matter that forms planets and chemistry and biology, occupy the remaining fraction. The universe is, by volume, mostly nothing. The something is a thin web stretched across an enormous emptiness, and we live on a small rocky body attached to an ordinary star in one of the filaments of that web. A reasonable objection at this point is that the voids are not nothing. They contain the small number of galaxies mentioned earlier. They contain dark matter, distributed more thinly than in the filaments but present. They contain the cosmic microwave background radiation, the same everywhere. They contain dark energy, which appears to be a property of space itself, and therefore fills the voids as completely as it fills anywhere else. What the voids lack is the concentrations of ordinary matter that form stars and planets. They are not absolute emptiness. They are the quietest regions of a universe that is never fully quiet. Dark energy is the reason the voids are growing. The expansion of the universe is not uniform in its effects. In regions dense enough for gravity to dominate, like galaxy clusters, the gravitational attraction between objects is strong enough to resist the expansion. Those regions are not expanding internally. They are gravitationally bound. But in the voids, where matter is sparse and gravity is weak, the expansion proceeds essentially unchecked. The voids grow over time, not because matter is moving out of them rapidly, though some of that happens, but because the space within them is expanding, while the space within gravitationally bound structures is not. The web is stretching at its emptiest points, while holding roughly fixed at its densest ones. Over billions of years, this means the voids will become larger and emptier. The filaments will become more isolated from each other, and the overall structure of the cosmic web will become more pronounced, even as the universe as a whole becomes more diffuse. The Boötes Void of 10 billion years from now will be larger and emptier than the Boötes Void of today, assuming it continues to evolve as current models predict. There is a description of Paris that I have encountered in architectural writing, the idea that the city's famous underground catacombs, the network of tunnels and chambers running beneath the streets, are not merely beneath the city but are structurally necessary to it. The limestone quarried to build the city above created the caverns below, and those caverns now drain groundwater and provide a foundation of known, mapped space that allows the structures above to stand safely. The absence below is what makes the presence above possible. The cosmic web works on a related principle, though the relationship is different in its details. The voids are not structurally supporting the filaments in the way catacombs support streets, but the voids and the filaments are two aspects of the same process. The matter that is not in the voids is in the filaments. The emptiness of the voids is not the absence of a process, but the outcome of the same gravitational process that built the filaments. The web is defined as much by where the matter is, not as by where it is. Remove the voids, and you do not get a universe full of matter. You get a universe where the concept of structure has no meaning, because structure requires contrast, and contrast requires some places to be denser than others, which requires other places to be emptier. The voids are not the background against which the universe happens. They are part of what the universe is. The matter in your body came from somewhere in this web. The atoms were synthesized in stars, scattered by stellar deaths, collected into the molecular cloud that formed this solar system. That molecular cloud was part of a filament, a dense region of the web where gravity had concentrated enough matter for stars to form in sufficient numbers over sufficient time for the chemical enrichment required for rocky planets and water-based chemistry to be possible. If this solar system had formed inside a void, inside one of those vast, underdense regions, the story would have been different in ways that are difficult to fully specify, but that likely include the absence of anyone to tell the story. Void galaxies exist, but they are typically smaller, less chemically enriched, with star formation histories that differ from galaxies in denser environments. The thread connecting the large-scale structure of the universe to the conditions for biology is not direct or simple, but it is real. The Boötes Void is close enough, in cosmological terms, that the light we receive from the few galaxies within it left those galaxies when the universe was roughly half its current age. We are seeing those galaxies as they were approximately 7 billion years ago. Whether they have changed significantly in the intervening time, whether they have merged, whether star formation within them has continued or slowed, we do not know from direct observation. We are seeing old light from a region that we know to be unusual, and we are inferring its current state from models rather than from evidence that has had time to reach us. This is a constraint that runs through all of observational cosmology. The observable universe is not the current universe. It is the universe as it was at various distances back in time, because the speed of light is finite and the universe is large. When we map the cosmic web, we are mapping a structure that existed at different moments in cosmic history depending on how far away each part of it is. The map is a cross-section through time as much as through space. Lying still right now, in the dark, the voids are all around you in every direction, at various distances, growing slowly as dark energy stretches the space within them. The filament you inhabit, the local group of galaxies and the larger supercluster surrounding it, is gravitationally bound enough to resist that expansion on local scales. The Milky Way and Andromeda are moving toward each other. The local group is held together, but the void on the other side of the nearest filament is moving away. And the filament beyond that void is moving away faster, and the web is becoming more open, more diffuse, more spread across a volume that is itself growing. The something is getting thinner. The nothing is getting larger. Both are consequences of the same physics. There is a further question that the voids raise, and it concerns the matter that is not ordinary matter. The filaments contain far more mass than the visible galaxies within them can account for. The rotation curves of galaxies within those filaments, the way stars orbit at speeds that require more gravitational pull than the visible matter can provide, point to the presence of something massive and invisible threaded through the structure. Dark matter, whatever it is, traces the cosmic web. It is more concentrated in the filaments and clusters, less concentrated in the voids. The web we can see in galaxy surveys is a luminous tracer of a darker, more massive web underneath it, and the darker web is what gravity actually built. The galaxies are lit markers on a structure whose main component remains unidentified. You are lying inside a filament of that structure, on a planet orbiting a star, in a galaxy that is itself a small luminous node in a web whose dominant constituent has not yet been characterized. The emptiness around the filament is real. The matter in the filament is real. The dark matter threading through both is inferred from its gravitational effects and has not been directly detected. 3 facts about the same structure, each one established by different methods, each one carrying its own uncertainties, each one pointing toward the same conclusion. The universe at the largest scales is organized by processes that are mostly invisible and that have been running since before the first stars formed. If the structure that made chemistry and biology possible is itself a thin web stretched across a mostly empty universe, built from matter that is mostly invisible and growing more diffuse as the space within its emptiest regions expands, what does it mean that one small node of that web became aware of the web itself? Something is holding the galaxies together that should not be there. This is a description of a measurable discrepancy that has been sitting in the data for nearly a century, confirmed by multiple independent methods, and still not explained in terms of any particle or field that has been directly detected. The first person to take the discrepancy seriously was Fritz Zwicky, a Swiss astronomer working at Caltech in the early 1930s. Zwicky was measuring the velocities of galaxies within a large cluster, the Coma cluster, roughly 320 million light-years from Earth. He used the Doppler shift of the light from those galaxies, the same principle that makes an ambulance siren pitch higher as it approaches and lower as it recedes, to determine how fast the galaxies were moving relative to the cluster's center. The velocities were too high. By too high, the physics means something precise. A cluster of galaxies is held together by the mutual gravitational attraction of all the matter within it. If you know how much matter is present, you can calculate how fast the member galaxies can be moving before their kinetic energy exceeds the gravitational binding energy and the cluster flies apart. The galaxies in the Coma cluster were moving fast enough that, given the amount of visible matter in the cluster, they should have dispersed long ago. The cluster should not exist. Zwicky proposed that the cluster contained a large amount of invisible mass that contributed to the gravitational binding but did not emit or reflect light. He called it Dunkel materia, dark matter. The proposal was noted and largely set aside. The tools to test it thoroughly did not yet exist, and the idea that most of the matter in the universe might be invisible was difficult to absorb without compelling evidence beyond one cluster measurement. The compelling evidence came 4 decades later through a different method and a different astronomer. Vera Rubin was working with the spectroscopist Kent Ford in the late 1960s and into the 1970s, measuring the rotation curves of spiral galaxies. A rotation curve is simply a plot of how fast stars orbit the center of a galaxy as a function of their distance from that center. The expectation, based on the visible distribution of matter in a spiral galaxy, was clear. Stars near the center, where most of the mass is concentrated, should orbit quickly. Stars in the outer regions, far from the concentrated mass, should orbit more slowly, the same way the outer planets in our solar system orbit the Sun more slowly than the inner ones. Mercury moves faster than Neptune because Mercury is closer to where most of the solar system's mass sits. The outer stars in spiral galaxies were not moving more slowly. They were moving at roughly the same speed as stars much closer to the center, or in some cases faster. The rotation curves were flat, where physics said they should fall. The only explanation consistent with the observed velocities was that the mass distribution in these galaxies did not match the visible distribution. There had to be mass in the outer regions, distributed in a roughly spherical halo extending well beyond the visible disk of stars and gas, contributing enough gravitational pull to keep the outer stars moving at the speeds observed. The halo was not visible. It did not emit light in any wavelength the instruments could detect, but the motion of the visible stars traced its presence as clearly as the bent path of light traces the presence of glass. Rubin knew her results were right from the late 1960s. Getting the broader community to take them seriously took years. The data was good. The analysis was careful. The implications were uncomfortable in a way that made some people look for alternatives before accepting what the measurements showed. By the late 1970s, the alternatives had been tested and had not held up. The rotation curves were real. The invisible mass was real. The question shifted from whether dark matter existed to what it was. That question has not been answered. What has been established is a detailed picture of what dark matter does, even without knowing what it is. It accounts for roughly 27% of the total energy content of the observable universe. Ordinary matter, everything made of protons, neutrons, and electrons, accounts for roughly 5%. The remaining 68% is dark energy, the name given to whatever is causing the expansion of the universe to accelerate. Dark matter does not emit light, does not absorb light, does not interact with the electromagnetic force in any way that has been detected. It interacts with gravity, and possibly with the weak nuclear force. And through those interactions, it shapes the large-scale structure of the universe and the dynamics of individual galaxies. The most direct evidence that dark matter is a real physical substance rather than a modification of how gravity works came from an observation of two galaxy clusters colliding. When two clusters pass through each other, their ordinary matter, the hot gas that makes up most of the visible mass in a cluster, interacts electromagnetically. It heats up, slows down, and lags behind the galaxies themselves, which pass through each other like two swarms of bees, the individual galaxies too widely spaced to collide directly. The gas piles up in the middle of the collision zone. If dark matter were a property of the distribution of ordinary matter, it would pile up too. In the system called the bullet cluster, the dark matter did not pile up. It was mapped through gravitational lensing, the bending of light from background galaxies by the mass of the cluster, and it showed two distinct concentrations that had passed through each other and continued moving with the galaxies. The gas, the ordinary matter, was in the middle. The dark matter was out ahead, on either side, in two halos that had passed through each other without slowing down. This is what a substance that does not interact electromagnetically does when two concentrations of it collide. It passes through itself. The dark matter halos of the two clusters move through each other the way two beams of light cross without deflecting. The gas, which does interact electromagnetically, got stuck in the middle. The separation was clean enough that the bullet cluster observation is considered the most direct evidence available that dark matter is a distinct physical substance, not a modification of gravitational theory. The two components of the cluster went to different places because they interact with the world differently. What dark matter is made of remains unknown. The leading candidates are particles that have not yet been detected in any laboratory. Weakly interacting massive particles, called WIMPs, were the frontrunner for decades, predicted by extensions of the standard model of particle physics and expected to produce a detectable signal in underground detectors shielded from cosmic ray background. The detectors have been running, with increasing sensitivity, for decades. They have not found WIMPs. The absence is not conclusive. It constrains the possible mass and interaction strength of the hypothetical particle, ruling out the parameter space that has been searched and pushing the search toward regions that require more sensitive instruments. But the longer the search continues without a signal, the more seriously the alternatives must be taken. Axions, sterile neutrinos, primordial black holes formed in the early universe, modifications to gravity that work differently at large scales than at small ones, all remain possibilities that have not been ruled out. 27% of the universe, by energy content, is made of something whose identity is unknown after nearly a century of effort to characterize it. The detection methods have been varied, the experiments have been careful, the theoretical work has been extensive, and the thing itself has not been caught. It shows up only in what it does to everything around it, never in any direct interaction with instruments designed to catch it. Vera Rubin spent the rest of her career after the rotation curve work continuing to observe, continuing to collect data, and continuing to argue for the importance of what the data showed. She died in December of 2016 without the Nobel Prize that many of her colleagues believed the work deserved. The Nobel Committee does not award prizes posthumously. The dark matter whose existence she helped establish is passing through this room right now. Through the walls, through the floor, through the body you are lying in, billions of dark matter particles, if the leading models are correct, stream through every square centimeter of surface on Earth every second, interacting with nothing, leaving no trace, continuing outward through the planet and into space on the other side. The number is not a rough estimate. The calculation follows directly from the known density of dark matter in the vicinity of the solar system and the Earth's velocity through the dark matter halo of the galaxy. They are there. We have simply not yet built an instrument sensitive enough to catch one in the act of the rare interaction that would reveal it. The history of physics includes several instances where something invisible was proposed to account for a discrepancy, and the invisible thing was eventually found. The planet Neptune was predicted from anomalies in Uranus's orbit before it was observed. The neutrino was proposed to account for missing energy in radioactive decay before any detector was sensitive enough to catch one. In both cases, the invisible thing turned out to be real and was eventually confirmed. Dark matter may follow the same path. The evidence for its gravitational effects is robust enough that most physicists treat its existence as established, even while its identity remains open. What is not guaranteed is that the particle approach is correct, or that the leading candidates are the right ones, or that the detection methods currently being pursued are sensitive to whatever dark matter actually is. The rotation of the galaxy you are inside is being shaped right now by a substance whose nature is unknown. The filament of the cosmic web that contains this galaxy exists in the shape it does because dark matter halos collapsed first, providing the gravitational scaffolding into which ordinary matter fell to form the visible structure. The stars in the Milky Way follow orbits determined in part by a halo of invisible material extending far beyond the visible disk. The conditions that allowed this solar system to form, this planet to retain its atmosphere, this chemistry to run, depended on a gravitational environment shaped by something that has not yet been characterized. The anchor is real. We are held by something we cannot see and have not named. If dark matter shaped every structure in the observable universe and remains unidentified after nearly a century of increasingly sensitive searches, what does that imply about the completeness of the inventory we have taken of what exists? The universe began hot enough that the distinctions between the fundamental forces of nature did not exist. Not weakened, not difficult to observe, genuinely absent, in the sense that the conditions required for those distinctions to appear had not yet been established. In the first fractions of a second after the Big Bang, the temperature was high enough that the electromagnetic force and the weak nuclear force behaved as a single unified interaction. Particles that are now distinct had not yet acquired the properties that make them distinct. The universe was a state of symmetry so complete that the variety of the world we inhabit had not yet emerged from it. Then it cooled. As the temperature dropped, the unified state became unstable and the forces separated. This process is called symmetry breaking, and it has a precise analogy in something that happens in kitchens and in physics laboratories at temperatures far less extreme. When liquid water cools through 0 degrees Celsius, it freezes. The liquid state has a rotational symmetry that the solid state does not. A liquid looks the same from every direction. A crystal of ice has preferred axes, preferred planes, a structure that distinguishes some directions from others. The symmetry of the liquid breaks when the solid forms, and the resulting crystal is less symmetric than what it came from. But crystals do not form uniformly. Different regions of the liquid begin to freeze at different times, oriented in different directions. Where two regions growing from different nucleation points meet, the crystal structures do not align. A boundary forms between them, a line of mismatch where the two differently oriented regions encountered each other and could not reconcile their structures. In ice, these boundaries are visible as cracks or inclusions. In metal alloys cooled from a melt, they are called grain boundaries, and they affect the mechanical properties of the material in ways that engineers have to account for. The boundary is not a defect introduced from outside. It is a consequence of the geometry of how the transition happened. Two regions that froze independently, oriented differently, leaving a permanent record of the fact that they did not coordinate. The theoretical prediction is that something analogous happened in the early universe, at scales and energies incomparably larger, during the symmetry-breaking transitions of the first fraction of a second. Different regions of the early universe, causally disconnected from each other because the universe was expanding faster than light could travel between them, would have undergone the symmetry-breaking transition independently, settling into different orientations of the broken symmetry. Where those regions eventually came into causal contact, the boundaries between differently oriented regions could not simply merge. The geometry of the broken symmetry in some cases requires a line of unbroken symmetry to persist where the boundaries meet, threading through space, carrying the energy of the original unified state in a one-dimensional structure that cannot dissolve without the regions on either side rearranging themselves globally. These are cosmic strings. Not strings in the sense of string theory, which operates at a different scale and involves different physics, though the terminology overlaps in a way that causes confusion. Cosmic strings are topological defects, one-dimensional structures embedded in three-dimensional space, predicted by certain classes of field theories describing the early universe. If they exist, they would be extraordinarily thin, with a width comparable to a proton, roughly 1 femtometer. A femtometer is 1 quadrillionth of a meter. If a cosmic string were scaled up to the width of a human hair, the hair scaled by the same factor would span roughly 10 times the distance from here to the Andromeda Galaxy. The thinness is one extreme, the other is the mass. Because a cosmic string carries the energy density of the unified state compressed into its cross-section, its mass per unit length is extraordinary. The precise value depends on the energy scale of the symmetry breaking that produced it. But in the models that produce strings observable through their gravitational effects, the mass per unit length would be roughly 10 million billion tons per centimeter. A single centimeter of cosmic string, if you could hold it, which you could not for reasons that go well beyond the obvious, would outweigh every mountain range on Earth combined by a factor of roughly 1,000. A string of that mass density, extended across cosmological distances, would curve space-time around it in a distinctive way, not the way a point mass curves space-time into a bowl shape, but something geometrically different. A long, straight cosmic string produces no gravitational attraction toward it in the usual sense. Instead, it removes a wedge of space around itself, the way a cone is formed by removing a wedge from a flat sheet and rejoining the edges. This means that two particles passing on opposite sides of a cosmic string would be deflected slightly toward each other. Not because the string is pulling them, but because the geometry of space in the string's vicinity is missing an angular wedge. The observational signature of this is distinctive enough that astronomers have searched for it. The most direct method is to look for pairs of images of background objects, quasars or galaxies, that have been gravitationally lensed into two nearly identical copies by an intervening cosmic string. A point mass lens produces arcs or rings. A string lens produces two images of the source with specific geometric properties related to the string's orientation and the angle of the deficit. Several candidate events have been reported over the decades. None has been confirmed with sufficient certainty to constitute a detection. Pulsar timing arrays offer another approach. A network of millisecond pulsars distributed across the sky, monitored over years for correlated deviations in pulse arrival times, is sensitive to gravitational waves with wavelengths measured in light years. A network of cosmic strings moving through the universe would produce a background of gravitational waves with a spectrum that differs from other proposed sources. Recent results from pulsar timing array collaborations have reported evidence for a gravitational wave background at the relevant frequencies. Whether that background has the spectrum expected from cosmic strings, or from the inspiral of supermassive black hole binaries, or from some combination, is currently being analyzed. The data does not yet distinguish clearly between the candidates. The data exists. The signal is there. The question of what produced it is genuinely open, and cosmic strings are genuinely among the candidates. This is not a situation where the evidence clearly favors one explanation, and other possibilities are being entertained as courtesy. This is a situation where the evidence is not yet precise enough to tell the difference between several physically distinct explanations. The prediction that cosmic strings should exist does not come from speculation. It comes from the same class of field theories that successfully predicted other aspects of particle physics. If the symmetry-breaking transitions of the early universe proceeded in ways consistent with those theories, and if the geometry of the broken symmetry satisfies the topological conditions required for stable defects, then cosmic strings are a necessary consequence, not a possible consequence, a necessary one. The theoretical machinery that produces them is the same machinery that correctly describes the behavior of superconductors and liquid crystals here on Earth, where analogous topological defects, called vortices and disclinations, are observed directly. What makes cosmic strings interesting is not just what they are, but what they remember. A cosmic string, if it exists, carries in its structure the conditions of the universe as it was in the first tiny fraction of a second after the Big Bang. It is a relic of a state of symmetry that no longer exists anywhere else in the observable universe. The forces are separated everywhere else. In the string, if the theoretical picture is correct, they are still unified, still running as a single interaction, preserved by the topological constraints that prevent the string from simply dissolving into the lower symmetry state of the surrounding space. A crack in the ice, still carrying the memory of water. The universe we inhabit is the broken symmetry state. The variety of particles, the distinct forces, the different interaction strengths that make chemistry and biology possible, all of that emerged from the breaking of a more symmetric state. The strings, if they exist, are the places where that breaking was incomplete, where the original state persists in a one-dimensional line threading through the fabric of what came after. They are not imperfections in an otherwise perfect universe. They are the residue of the process that made the universe what it is. We are looking for the scars of the beginning. We are trying to find the lines where the early universe's transition from one state to another left a permanent record, a boundary that could not be healed, an encoding of conditions that no longer exist anywhere else. The search for cosmic strings is a search for a direct record of the universe before it became what it is now. Whether that record exists in a form we can detect is not yet known. The theoretical prediction is solid enough to take seriously. The observational search has been running long enough to rule out the most extreme versions and constrain the parameter space of the survivors. The current pulsar timing results are ambiguous enough to keep the question open. The next generation of instruments, more sensitive, monitoring more pulsars over longer baselines, will either find the signature or constrain it further. What would it mean to find it? A direct detection of cosmic strings would confirm that the symmetry-breaking transitions of the early universe proceeded in a way that left topological defects, which would constrain the class of field theories describing those transitions, which would narrow the space of possible theories, unifying the fundamental forces. It would be a detection of a structure formed in the first fraction of a second of the universe's existence, still present after nearly 14 billion years, threading through the space between galaxies, carrying the imprint of a state that no longer exists. It would be, in a precise sense, a message from before the universe had settled into being what it is. A message that has been traveling for nearly 14 billion years, in a form we are only now developing the instruments to read. The oh my god particle arrived and dissolved in microseconds. The pulsar signal arrived and was noticed by someone paying close attention. Cosmic strings, if they exist, have been present since the beginning, threading through the structure of everything, waiting for instruments sensitive enough to read the gravitational signature they leave in the timing of distant pulsars. The beginning left marks. We are still learning to see them. If the symmetry-breaking transitions of the early universe left permanent topological scars threading through space, and if those scars carry the imprint of conditions that no longer exist anywhere else, what other records of the beginning are embedded in the structure of what came after, waiting for the right instrument and the right attention? The universe, in its first moments, had a problem. Several problems, actually, and they were not small ones. They were the kind of problems that, if you encountered them in a physical theory without a solution, would suggest the theory was wrong. The universe we observe is too flat, too smooth, and too free of certain exotic relics that the physics of the early universe predicts should have been produced in abundance. Each of those three anomalies, taken alone, might be a measurement uncertainty or a gap in understanding. Together, they pointed to something missing from the picture. The flatness problem is the most precise to state. The geometry of space, whether it curves back on itself like the surface of a sphere, or opens outward like a saddle, or lies flat like an infinite plane, is determined by the total energy density of the universe relative to a critical value. If the density is exactly at that critical value, space is flat. If it departs from it, space curves, and a curved universe evolves differently over time in ways that become increasingly pronounced. The observable universe today is flat to within measurement precision of roughly 1%. That sounds like a reasonable state of affairs until you run the physics backward in time and ask what the density had to be in the first second of the universe's existence to produce the flatness we observe now. The answer is that the density in the first second had to match the critical value to within roughly 1 part in 10 to the 15th. 1 part in a quadrillion. If it had been higher by that margin, the universe would have collapsed back on itself long before stars could form. If it had been lower, space would have expanded so rapidly that matter could never have concentrated enough to form anything. A universe balanced to 1 part in a quadrillion in its first second, without any mechanism to explain why it was balanced that way, is a universe asking you to accept an extraordinary coincidence. Physics is generally uncomfortable with extraordinary coincidences. They usually indicate that something is being left out of the explanation. The smoothness problem is equally uncomfortable. The cosmic microwave background, the oldest light in the observable universe, released when the universe cooled enough for electrons and protons to combine into neutral hydrogen roughly 380,000 years after the Big Bang, is uniform in temperature across the entire sky to roughly 1 part in 100,000. Regions of the sky that are separated by angles large enough that, at the moment the light was released, they could not have been in causal contact with each other because the universe had not been old enough for light to travel between them, have the same temperature to that precision. Two regions that have never been able to exchange energy or information should not be expected to be at the same temperature. Temperature equilibration requires contact. If you put a hot object and a cold object in contact, they will eventually reach the same temperature. If they have never been in contact, there is no mechanism to equilibrate them. And yet the sky is smooth, in every direction, to a precision that cannot be explained by any equilibration process if those regions were truly causally disconnected at the moment the light was released. Alan Guth was a young particle physicist in December of 1979, working through implications of certain field theories for the behavior of the early universe, when he arrived at a calculation whose consequences he recognized immediately. His notebook from that night contains the words, "spectacular realization," underlined twice. The realization was this: if the very early universe underwent a period of extraordinarily rapid exponential expansion, driven by the energy of a quantum field in an unstable, high-energy state. That expansion would solve both problems simultaneously. Consider what exponential expansion does to geometry. Take a curved surface and expand it by a factor large enough, and any region small enough to be observed becomes indistinguishable from flat. The surface of the Earth is curved, but a patch of ground the size of a parking lot looks flat because the curvature is spread across a much larger surface. Inflation would have expanded the observable universe from a region far smaller than a proton to something roughly the size of a grapefruit in an interval estimated at somewhere between 10 to the minus 36 and 10 to the minus 32 seconds. A region that was flat enough to begin with, expanded by that factor, would appear flat to any measurement possible from within it. The flatness is not a coincidence requiring explanation. It is a consequence of the expansion. The smoothness follows from the same mechanism. The region that expanded to become the observable universe was, before inflation began, small enough that it had been in causal contact with itself. It had time to equilibrate. The expansion then stretched that small, equilibrated region to the scale of the observable universe, preserving the uniformity across scales that are now causally disconnected from each other because the expansion moved them apart faster than light could maintain contact between them. The sky looks the same in every direction not because disconnected regions somehow coordinated, but because they were all part of the same small region before inflation separated them. The observable universe, everything within roughly 46 billion light-years of Earth, all of it, grew from a region smaller than a proton in a time interval so short that no unit familiar from daily experience conveys it usefully. 10 to the minus 36 seconds. If you divided 1 second into 1 trillion equal parts, and then divided one of those parts into 1 trillion equal parts again, you would still need to divide by another trillion to approach the timescale involved. Inflation happened and was over before anything we would recognize as a physical process had time to complete a single cycle. The quantum fluctuations present in that initial region were stretched along with everything else. This is where inflation connects to everything that came after it, and the connection is not loose or approximate. It is causal and specific. The tiny variations in density that inflation stretched to cosmic scales became the seeds of all subsequent structure. Regions slightly denser than average attracted more matter, collapsed into the first stars and galaxies. Regions slightly less dense became the voids. The pattern of those initial fluctuations, written into the cosmic microwave background as temperature variations of roughly 1 part in 100,000, is visible in current observations and matches the predictions of inflationary models with a precision that makes the agreement difficult to dismiss as coincidence. The large-scale structure of the observable universe, the filaments and voids and clusters of the cosmic web, traces back to quantum noise in a region smaller than a proton, stretched to cosmic scales by a process that lasted less than a blink of anything. Every galaxy, every star, every planet, every arrangement of chemistry that has ever produced anything, all of it grew from fluctuations in a quantum field so small that the Planck length, the smallest meaningful unit of distance in current physics, is enormous by comparison. The mechanism that drove inflation, the quantum field whose energy density caused the expansion, is called the inflaton. It has not been identified with any known particle. The energy scale at which inflation occurred is high enough that it lies outside the range accessible to any particle accelerator built or planned. The details of how inflation began and ended, what the inflaton field actually is, whether inflation produced multiple regions with different properties expanding into a larger structure, these questions are active and genuinely open. The framework is constrained by observations. The interior of the framework is not yet fully characterized. There is a prediction that distinguishes inflationary models from alternatives, and it concerns gravitational waves. The violent, exponential expansion of inflation would have produced gravitational waves, ripples in space-time, at a specific amplitude and with a specific pattern of polarization imprinted on the cosmic microwave background. Detecting that pattern would constitute direct evidence of the inflationary process, a measurement of space-time fluctuations produced in the first tiny fraction of a second, preserved in the oldest light in the universe. Several experiments are currently searching for this signal. It has not yet been detected. The search constrains the energy scale of inflation and rules out some models while leaving others viable. The precision with which current observations agree with inflationary predictions is worth being clear about, because it is the reason physicists take the framework seriously despite the open questions. The spectrum of temperature fluctuations in the cosmic microwave background, measured across the full sky with instruments of increasing sensitivity over 3 decades, matches the predictions of the simplest inflationary models to a degree that would be extraordinary if the agreement were coincidental. Not every detail is perfectly accounted for. There are anomalies at large angular scales that remain unexplained, but the overall agreement is tight enough that inflation is now part of the standard cosmological model rather than a speculative proposal. That transition from speculative proposal to standard model happened within a single human lifetime. Guth's notebook entry is from 1979. The observations that elevated inflation to standard cosmology came in the following 4 decades. The people who developed the framework are still working. The observations that will test it further are being planned and built. Lying still right now, the oldest light in the universe is passing through this room. Photons of the cosmic microwave background, released 380,000 years after the Big Bang, carrying the imprint of fluctuations stretched from quantum scales by inflation, are crossing the space you occupy at the speed of light. They have been traveling for roughly 13.8 billion years. They pass through walls, through the roof, through the body you are lying in, and continue outward. The instruments that map their temperature and polarization detect them by the faint energy they deposit in cryogenically cooled sensors. You are immersed in the oldest signal in the observable universe. It passes through you continuously, carrying information about the first fraction of a second, and leaves no trace you can feel. The spectacular realization Guth had in December of 1979 connected a problem in cosmology to a mechanism in quantum field theory and produced a framework that explained, in one step, why the universe is flat, why it is smooth, and why the large-scale structure looks the way it does. The realization required following the mathematics into territory where intuition had nothing useful to offer, accepting the implications of equations that described a process no instrument could observe directly, and checking whether the observable consequences matched the data. They did. They still do. And the process that produced them lasted less time than any clock has ever measured, in a region smaller than any particle accelerator has ever probed, driven by a field whose identity remains unknown. If the entire visible structure of the universe grew from quantum fluctuations stretched by a process that lasted an immeasurably small fraction of a second, what does it mean that those fluctuations, rather than any other possible initial configuration, are the ones that produced a universe in which the fluctuations could eventually be measured? Everything that is happening right now is happening because of a difference. The candle burns because it is hotter than the air around it. The heart beats because one side of a cell membrane has a different ion concentration than the other. The star shines because its core is denser and hotter than the space surrounding it. Every process, every event, every instance of something occurring rather than not occurring runs on a gradient, something higher flowing towards something lower, something concentrated moving towards something dispersed. The event is the equalization. When the equalization is complete, the process stops. This is what the second law of thermodynamics describes, and it is the closest thing physics has to a statement about the direction of time. Entropy, the measure of how evenly energy is distributed across a system, does not decrease in a closed system. It increases or stays the same, but it does not go back. The gradient that drives a process is consumed by the process. Once consumed, it is gone. The candle that has burned cannot be unburned. The heat that has dispersed into the room cannot spontaneously reconcentrate itself back into the wick. The universe is a closed system, and it started with an extraordinary gradient. The early universe was in a state of low entropy, not because it was cold, it was in fact extraordinarily hot, but because its energy was concentrated, structured, far from the equilibrium that would represent maximum entropy at that temperature. The expansion of the universe has been a process of that gradient slowly being consumed. Stars are engines running on the gradient between the nuclear energy locked in hydrogen and the lower energy state of helium and heavier elements. They shine by running that gradient down. When the hydrogen is gone, the engine stops. The light goes out. The energy that powered the star is still there, dispersed as heat and radiation into the surrounding space, but it is no longer available to do work. Dispersed energy, energy without a gradient, is energy that cannot drive any further process. The universe has a finite amount of usable energy, and it is spending it. The timeline of this spending has been worked out in broad strokes, and the strokes are vast enough that any number given for them requires an immediate act of imagination to carry it all. The current era, in which stars are forming and burning across the observable universe, is called the stelliferous era. It will end in roughly 100 trillion years, when the last stars, the small, cool red dwarfs that burn their hydrogen so slowly and so carefully that they last 1,000 times longer than the sun, finally exhaust their fuel and cool into dark remnants. 100 trillion years. The sun will have been dark for roughly 99 trillion and 900 billion of those years before the last star goes out. If the entire history of the universe so far, 13.8 billion years, were compressed into a single day, the stelliferous era would last roughly 2 years. We are, by that measure, in the first few minutes of the morning of the first day. After the stelliferous era ends, what remains are the remnants. White dwarfs, slowly cooling, neutron stars, their pulsing long since slowed to silence. Black holes, the most stable objects the universe produces, persisting for timescales that make the stelliferous era look like a rounding error. A black hole of stellar mass, the kind produced by the death of a massive star, will evaporate through Hawking radiation, the slow thermal emission predicted by the combination of quantum mechanics and general relativity, in roughly 10 to the 67th years. That number is so large that writing it out in full as a 1 followed by 67 zeros conveys almost nothing useful. Consider it this way instead. If you wrote 1 digit per second, writing that number would take longer than the age of the universe. Then do that again. Then do that again, 65 more times. That is how long a stellar mass black hole persists before evaporating. The supermassive black holes at the centers of galaxies, objects millions or billions of times more massive, will take correspondingly longer. A black hole with a mass of 100 billion solar masses will evaporate in roughly 10 to the 106th years, a number that has no analogy capable of surviving contact with it. After the last black hole evaporates, what remains is a universe in which the energy that existed at the beginning has been distributed as uniformly as the laws of physics allow. No gradients, no differences in temperature or density large enough to drive any process, no events, a state of maximum entropy that physicists call the heat death, not because the universe will be hot, it will be extraordinarily cold, but because the heat, meaning the usable energy, will be fully dispersed. The heat death is not a dramatic end. It is the absence of anything dramatic happening, extended forever. No explosion, no collapse, no final moment. Just a universe in which nothing further occurs because nothing further can. Because the differences that would be required to drive any process have been exhausted. The second law of thermodynamics does not say that gradients are bad or that equilibrium is good. It says that gradients are consumed by the processes they drive, and that this consumption is irreversible. That is a statement about the direction of time and the structure of physical processes. Whether it is a statement about value, about whether the existence of the universe matters or fails to matter because of how it ends, is a question the physics does not answer and probably cannot. What the physics does say is that every gradient currently being consumed represents a process currently occurring. The nuclear reactions in stellar cores, the ion concentrations across cell membranes, the temperature difference between your body and the room you are lying in. Every one of those processes is real, is happening, is drawing on a gradient that took the history of the universe to produce, and that will not be available again in the same form once it is consumed. The impermanence of gradients is not their failure, it is their nature. A candle that burned forever would not be a candle, it would be a star, and even stars eventually go out. The burning is what the candle is. The gradient is what makes the process possible, and the process is what the gradient is for, in the only sense that for means anything in a physical system. There is a specific thing that strikes me about lying in a warm room while the universe is cooling. The body maintains a temperature of roughly 37 degrees Celsius, about 98.6 Fahrenheit, through continuous metabolic activity. That temperature difference between the body and the surrounding air, roughly 15 to 20 degrees on a cool night, is a gradient being actively maintained against the tendency of heat to disperse. The body spends roughly 80 watts of power just keeping that difference from collapsing, about the same as an incandescent light bulb. Sleep reduces the metabolic rate, but does not come close to eliminating it. The body, lying still in the dark, is still spending energy to remain warmer than the room. That gradient is the same phenomenon as stellar nucleosynthesis and galactic rotation, scaled down to the dimensions of a body in a bed. The universe running its entropy budget, the gradient being maintained for now, slowly consumed, eventually to be dispersed. The difference between the body and the room will outlast the body. The heat the body produces tonight will diffuse into the building, into the air, into the ground, and eventually into the larger heat budget of the planet, and the planet's excess heat will radiate into space, and the space it radiates into is getting colder. As the stars that warm it go out one by one over timescales no human intuition was built to hold. All of that is continuous with what is happening right now in this room. The same process, the same direction, the same irreversibility. Not a different physics operating at large scales. The same physics, the same law, applied to a body in a bed and to the observable universe and to everything in between. The proton decay predicted by certain extensions of the standard model of particle physics would, if it occurs, eventually eliminate the last baryonic matter remaining after the black holes have evaporated. The predicted timescale is roughly 10 to the 36th years for a proton to decay. Proton decay has not been observed. The experiments designed to detect it have been running for decades in underground tanks of ultra-pure water, waiting for the faint flash of Cherenkov radiation that would indicate a proton has spontaneously converted into lighter particles. Nothing yet. The non-observation constrains the models, but does not rule out eventual decay on longer timescales. Whether protons are stable forever or decay eventually, the endpoint is the same. A universe in which the energy budget has been fully dispersed, the gradients consumed, the processes completed. Not darkness in the dramatic sense, something quieter. A state in which the concept of darkness has lost its referent, because darkness is defined relative to light, and light requires a gradient to produce, and gradients will be gone. What remains in that state is harder to characterize than the physics of its production. The laws of physics themselves, the mathematical relationships that govern how matter and energy behave, are not made of matter or energy. They do not require a gradient to persist. Whether they persist in any meaningful sense in a universe with no processes to instantiate them is a question that physics, in its current form, cannot address. The laws describe processes. In the absence of processes, what the laws are is not clear. This is one of the places where the description runs out, not because the physics has been applied incorrectly, but because the question being asked is at the edge of what the physics is designed to answer. The second law describes the direction of entropy change in systems that exist. It does not describe what it means for a law to exist in the absence of systems to govern. The universe is spending its gradient right now, in every direction, at every scale. It has been doing so since it began. The spending is what produces every star, every cell, every thought. The budget is large enough that the spending has been going on for nearly 14 billion years and will continue for many orders of magnitude longer. But it is a budget, not an endowment. It is being drawn down, irreversibly, toward a state of equilibrium that will not support any further drawing. That process will not be completed tonight. It will not be completed in any interval of time that the human mind can genuinely hold. What will be completed tonight is a small part of the metabolic process that is keeping the body warmer than the room, drawing on chemical gradients established by the food consumed in the last several hours, maintaining the temperature difference that makes the warmth of the blanket feel like warmth rather than indifference. The warmth is real. The gradient producing it is temporary. Both of those things are true at the same time, and neither one cancels the other. If the universe began with a gradient that has been slowly consumed by every process that has ever occurred, and if the consumption is irreversible and will eventually be complete, what is the significance of any particular moment of spending in a budget that vast? You have been here the whole time. Not here in this room, though that too. Here in the sense that matters to physics, present, warm, processing, maintaining a gradient against a universe that is slowly and irreversibly moving toward the absence of all gradients. Your body has been doing this without asking your permission, without requiring your attention, through every act of this journey tonight. The heart has been beating. The neurons have been firing. The mitochondria in every cell have been running the same oxidative chemistry that has been running in living things for roughly 2 billion years, since the first cells learned to use oxygen as an electron acceptor and discovered that the energy yield was high enough to power everything that followed. The carbon in your body was forged in a stellar core. Not approximately forged there, not in a poetic sense. The specific atoms, the ones currently arranged into the proteins and lipids and nucleic acids that constitute the physical substrate of whatever you are experiencing right now, passed through the nuclear reactions of at least one star that died before this solar system existed. They were scattered by the explosion. They drifted through interstellar space as part of a molecular cloud. They collapsed with that cloud into a disk of material orbiting a young sun, accreted into a rocky planet, cycled through oceans and atmosphere, and early organisms and continental drift, and the slow chemical enrichment of a biosphere building complexity across 4 billion years. And they arrived here, in this arrangement, tonight. That is not a small thing to be. The observable universe contains somewhere between 100 and 200 billion galaxies. Each galaxy contains, on average, hundreds of billions of stars. The fraction of those stars that have produced arrangements of matter capable of lying in the dark and following an argument about the nature of time and entropy and the geometry of black holes is, as far as anyone can determine with current evidence, extraordinarily small. Not zero, almost certainly. But small in a way that the number of galaxies and stars does not compensate for, because complexity of this kind requires not just matter and energy, but a specific history of chemical enrichment, planetary stability, the right distance from the right kind of star, liquid water across geological timescales, and a chain of evolutionary contingencies so long that rerunning the history of this planet from the beginning would almost certainly produce something, but probably not this. The awareness in this room right now is, by the best available evidence, rare. Not precious in the sentimental sense, though that may also be true. Rare in the physical sense, in the sense that the conditions required to produce it are highly specific, and the universe does not reliably produce highly specific things. It produces variety. It produces abundance at the level of stars and galaxies. It is not generous with complexity at the level of nervous systems. Earlier tonight, the path led through the way the brain edits its own perception, through the evolutionary pressures that shaped what organisms can and cannot register about the world around them. It led through the question of what information survives the most extreme physical processes known to physics, and through the question of whether the choices made within a nervous system are as authored as they feel from the inside. Those questions did not resolve into clean answers, because they do not have clean answers available. What they did was describe, from several directions, what it is like to be a physical system complex enough to ask about its own nature and not complex enough to fully answer. That is the condition. Not a problem to be solved. The actual condition of being what we are. The cosmic microwave background is passing through this room right now, as it passes through every room on Earth and through every cubic meter of the observable universe. Those photons carry the imprint of quantum fluctuations stretched by inflation to cosmic scales, the seeds of every galaxy, every star, every arrangement of chemistry that has ever occurred. They have been traveling for roughly 13.8 billion years. They do not know they are being discussed. They do not know anything. They are photons of a specific temperature and polarization, following geodesics through curved spacetime, doing what photons do. The fact that somewhere along one of those geodesics there is a planet with a thin layer of air and liquid water and evolved nervous systems that can detect those photons, measure their temperature to 6 decimal places, and use the measurements to reconstruct the conditions of the first fraction of a second of the universe. That fact is not written into the photons. It is not a consequence the photons contain. It is something that happened in addition to the photons, separately, in a small corner of the observable universe, as a result of a long sequence of physical processes that were running on their own principles without reference to any outcome. The universe did not produce awareness in order to understand itself. It produced awareness as a byproduct of chemistry running under the right conditions, and the awareness, having appeared, turned itself toward the universe and began measuring. What has been measured, across the centuries of accumulated observation that this night has moved through, is a picture of extraordinary scope and extraordinary incompleteness simultaneously. The universe is 13.8 billion years old and was once smaller than a proton. It is mostly empty, and the emptiness is growing. Most of its matter is invisible and unidentified. Its expansion is accelerating under the influence of something that has been given a name and not a description. The fundamental forces were once unified and are now distinct, and the boundary between those two states may have left permanent marks in the fabric of space that we are only now developing instruments to read. The stars will eventually go out. The black holes will eventually evaporate. The gradients will eventually be consumed. None of that is complete. Every sentence in that list has open questions attached to it. Active research programs, measurements being planned, instruments being built. The picture is not finished. It will not be finished within any time frame relevant to this room. And yet there is something the picture already shows clearly enough to say plainly. The universe has been running for nearly 14 billion years, producing structure at every scale from subatomic to supercluster, spending its entropy budget across a timeline so vast that human experience cannot hold it directly. Within that process, in one small location, over a tiny fraction of the total time, a portion of the universe's matter organized itself into systems capable of noticing what was happening around them and asking why. The noticing is real. The asking is real. The answers, partial and provisional as they are real. What those answers reveal is not a universe designed for this outcome or indifferent to it. The physics does not support either framing. What they reveal is a universe that, given the right conditions and enough time, produces this among other things. The conditions were met here. The time was available. And here, tonight, the universe that produced the conditions is being described by the conditions it produced imperfectly, with instruments shaped by the same evolutionary pressures that shaped every other feature of the biology doing the measuring. The editing is still running. The scruff in the data is still where it has always been, waiting for someone to notice it and refuse to move on. The gradients are still being consumed. The dark matter is still passing through. The cosmic strings, if they exist, are still threading through the space between galaxies, carrying the memory of a symmetry that broke before the first star ignited. You have traveled through all of that tonight and arrived back in this room, in this body, in this particular arrangement of stellar material that has been here, waiting, while the universe expanded around it. The journey does not end with an answer. It ends with a clearer sense of the shape of the question, which is a different thing and, I would argue, a more honest one. The universe is not a problem that has been solved or is being solved. It is a structure that is being described, incompletely, by a part of itself, using tools that the structure produced. The description changes as the tools improve. The structure continues regardless. Tonight, the tools were language and attention, and the accumulated observations of people who looked carefully at things that did not fit and refused to dismiss what they found. Jocelyn Bell's scruff, Vera Rubin's flat rotation curves, the anomalous dimming of a star that ancient astronomers named after a demon because they had no other framework for its behavior. Friedrich Bessel's 18 months of patient measurement that ended with a number so large it required a new unit to speak about without absurdity. The women at Harvard who classified 350,000 stellar spectra for 25 cents an hour and built the foundation on which everything since has rested. The universe was described by all of them, and by the people before them, and by the people since. The description is ongoing. The body lying in this room is part of it, not because any particular insight is required tonight, but because the attention is there, and the attention is the thing that keeps the description moving forward rather than stopping. Sleep will come. The metabolic processes will slow but not stop. The heart will continue its 60 to 80 beats per minute through the night, roughly 100,000 beats before morning, each one a small gradient being maintained, a small amount of the universe's entropy budget being spent on keeping this particular arrangement of matter intact for another few seconds. The neural activity will shift from the patterns of waking attention to the patterns of consolidation and repair, the brain doing the maintenance work it can only do when the processing demands of conscious experience are reduced. The dreams, if they come, will be the brain finding patterns in its own signal, running the same pattern recognition systems that named the Horsehead Nebula after a horse and saw demons in the rhythm of an eclipsing binary, now turned inward, finding faces and narratives and connections in the data of the day. The same systems, the same tendency, the same bias toward meaning and noise that has been running in human nervous systems long enough to be part of what human nervous systems are. Outside this room, the universe continues. The Milky Way and Andromeda are moving toward each other at roughly 110 kilometers per second. In about 4.5 billion years, they will begin to merge, a process that will take several billion years more and will redistribute the stars of both galaxies into a new configuration that has been given the provisional name Milkomeda. The Sun will not survive to see it in its current form. None of the life currently present on Earth will survive to see it. The merger will happen without witnesses from this planet, driven by the same gravitational physics that has been governing the motion of matter since before the first star formed. That is not a cause for grief. It is a description of what 4.5 billion years means at the scale of galaxies. The timescale is so large that the absence of current witnesses is simply a fact about timescales, not a statement about value. What is happening right now, in this room, is happening at a timescale that matters to biology. Seconds, minutes. The slow deepening of breathing that comes with the approach of sleep. The body temperature settling into its nightly drop of roughly 1 degree. A circadian rhythm that evolved in organisms living under skies that darkened every 24 hours, regulated by photoreceptors in the eyes that detect the specific wavelengths of light that change at dusk, triggering the hormonal cascade that makes the body want to be horizontal and still and quiet. The body knows what night is. It has known for a very long time. The universe does not know what night is. It does not know what day is, or what a year is, or what a lifetime is. Those are the timescales of organisms on the surface of a rocky planet, orbiting a particular kind of star at a particular distance. And they are real timescales, real durations, real intervals during which real things happen to real systems. They are not less real because the universe operates on longer ones. They are differently scaled expressions of the same physics, the same irreversible flow from lower entropy to higher, the same spending of gradients that were established at the beginning and have been running down ever since. The gradient in this room tonight includes the warmth of the body, the slightly cooler air, the processing that is slowing towards sleep, the breath moving in and out at its own rhythm. All of it is the universe doing what the universe does, locally, temporarily, in a configuration that will not persist indefinitely, but that is, right now, doing exactly what it is constituted to do. There is nothing left to explain tonight. Not because the explaining is finished, but because the night has its own physics, and the physics of this particular night says that the body needs what the body needs, and the mind has gone as far as it usefully goes, and the next thing that happens should be the kind of thing that happens in the dark, when everything that can be thought has been thought, and what remains is the simple fact of being here, warm, in a universe that is very large and very old and mostly empty and still, in this one small location, briefly, improbably, inhabited. Thank you for traveling this far. That is not a formality. Every part of this journey required someone at the other end willing to follow the argument into territory where the familiar frameworks stop helping and the only tools left are attention and honesty about what the evidence actually shows. You brought both of those tonight. The carbon in your body has been part of stars. Tonight it gets to rest.